Okay, could I ask you to take your seats, please, if you haven't already, and we'll kick off. Well, that killed the conversation. Okay, welcome everybody. Visitors, colleagues old and new, students, members of the team. I'm delighted to welcome you all here today for this symposium on AI and the future of engineering. My name is Beverly Gibbs and I'm Director of the Dyson Institute. So by way of welcome, I'm going to tell you a little bit about where we came from and what we do and what our plans are. There will be a presentation about the student program a little bit later, which our students will present. So I'm not going to talk about the program too much, but I will tell you about us as an institute. So the story about how the Dyson Institute came about, the one that you might have heard is probably the real one, which is that Sir James Dyson was complaining about a shortage of engineers, a shortage of good engineers, a shortage of work-ready engineers to ministers in government. And so Joe Johnson, who was then Minister for University, said, well, why don't you make your own university then? And being James Dyson, he said, OK, then I will. And so this was facilitated by the Higher Education and Research Act 2017, which some of you may know opened up a single pathway for registration of new universities. And so under that remit, the Dyson Institute opened in 2017 and welcomed 33 undergraduate engineers. In 2020, initially we were working in partnership with the University of Warwick Manufacturing Group, and had a fabulously productive relationship with them. In 2020, the Institute gained new degree awarding powers, also under the Higher Education and Research Act, which meant that we could register students directly onto a Dyson Institute degree. So since 2020, all of our students have been registered on a Dyson Institute degree. So in 2021, our first students graduated, and that was a moment of real celebration. And our first fully Dyson students joined us. 2023, we had some changes in leadership. So I joined at that point. Where's Peter? Peter Wilson also joined in 2023, and Peter's going to speak after me. He's our Deputy Director Academic, and we both joined the Institute last year. We also launched our 2028 strategy last year, and I'm going to tell you a little bit about what's in that and give you a QR code if you want to go and have a look at that. This year, we've had some fabulously good news. We've received full degree awarding powers, which means that we're out of the probationary period. And it means that we can expand our portfolio, which is something that we wanted to do. We were inspected by Ofsted after much waiting, and were thrilled to receive a rating of outstanding for our apprenticeship provision across all categories. And we were accredited by the IET for iEng and partial CEng for our engineering programme. This year, in September, we've withdrawn from a degree apprenticeship programme, and we will be launching an employer-sponsored MEng programme from September. So our new students, that's what they'll be registered to do. We're also launching an MSc software engineering conversion programme from September. So the team are busy in the final selection stages for those students. And we'll also be starting in the coming months a programme for Dyson engineers to do part-time micro-credentialed learning through to master's degree. So that's the history of the Institute, where we are in our development sort of programme. So let me tell you a little bit about the 5-year strategy. It's structured in 6 themes, really. So the first one is learning and teaching. So we remain committed to outstanding and innovative learning and teaching experience, where we are known for the industrial relevance of our degrees, and we share what we learn about how students learn, what immersive learning looks like, what industrial relevance might really mean, and we share that amongst the sector in the conversations that are already happening around those. We want to expand our portfolio of taught programmes and support the development of Dyson talent, so people who are already working here through programmes to upskill, reskill, reposition their skill set consistent with Dyson's technical strategy. Student experience is always important to us. In a small institute, we have extremely high standards for wanting a really, really good student experience. We know that that is key to the great things that our students go on to achieve. We have very high attainment levels, retention and progression levels, and so we keep listening to our students and keep trying to get it right all the time. It's an ongoing I don't want to say struggle, ongoing project, shall we say, as anybody who teaches knows, and we're very happy to work in partnership with our students in continually improving the student experience. Our community is important to us, so we work, as you may have gathered, our students are also our colleagues because they're Dyson employees, and so that does kind of change our relationship together. So we work together for the success of the Institute and for the success of Dyson. We also want to move now into research with having full degree awarding powers. This is the point at which we kind of share our commitment to research. This is a global headquarters for research and development for a global consumer electronics brand, essentially. And so we think that it's the right thing for our academic team and our student body to be in an environment where research is taking place. So ultimately, that will hopefully lead to the award of research degree awarding powers. That is a very long process and it takes some time, but that's the destination that's on our journey there. International, we are a global company. We want all of our talk programs to facilitate international experience. That looks like different things in different programs. Tansy, who's going to talk later, is about to go to Singapore very shortly, so they go over for the summer and work on a project there. She'll tell you a little bit more about that when she does. So that's one example of international working. In the workplace, our students are frequently working as part of global collaborative teams or have shadow teams, and so that is kind of embedded in their experience from day one. But also we want to make sure that the benefits of what we do here in the Institute and the opportunities that we give are open to all Dyson colleagues wherever they may be in the world, and so we take that on as a challenge to be able to deliver and offer that. And then finally, people and infrastructure. We want to realise the potential of all of our team members. We have good working relationships because we're a small institute, so we all know one another. We know our strengths and weaknesses and aims, and it's really important to us that we try and facilitate as much progression, expansion, enrichment as possible. We have a team that is leaning very hard into smart campus philosophy of what we do. You can see how that might fit with internationalisation ideas of working with different modes of learners, and so we have a team that is looking at the physical and digital sort of learning environment and robust governance arrangements. So some of you that are slightly more interested in how higher education's work will appreciate the challenge but the opportunity that comes with being an autonomous higher education provider, but which is embedded as part of a global company. That requires very robust governance to make sure that we all remember what we're doing and which hat we're wearing at any one time. And that works well, but it's something that we absolutely remain committed to doing. And then finally, the reason why we're here is for our integration with Dyson. We want to be, the Institute wants to be Dyson's key partner in the recruitment, development and retention of engineering talent. We want our students and graduates to be having a significant and notable impact in Dyson around the world. And so that's something now our graduates have started to move into permanent roles that we've started to capture. And there's some really exciting stories there that we see that tells us something about what exactly is happening in the Institute, and so that we can learn and build from that. And we want people in Dyson to be proud of what we do, just as we're proud of what they do. So that's a little run through just to introduce you to the Institute and what we are here. If you want to have a look at our 2028 strategy, there's a QR code there. It's also on our website, so do feel free to go and have a look. But other than that, I think I'm going to hand straight over to Dr. James Wilson, who is going to chair this morning's sessions. Welcome, everyone.
Cool. Okay, fantastic. So yeah, welcome to our first symposium on AI and the future of engineering. Our first speaker is going to be Professor Peter Wilson, our own Deputy Director of Academics, and his talk will be on the using computational intelligence techniques to accelerate design and automation. So I'll hand over.
Okay, thanks, James. Everyone. So just looking through the agenda, so just to, you may have seen that initially it was Tom Crick, but unfortunately as a scientific officer, he is now embargoed from speaking because of this weird election thing. So apologies for the change. I'm playing the substitute card here today. So as Beverly was saying, thanks for the intro, I'm heading up the academic team, and I've been working in design automation, computational intelligence, robotics for many years. Computational intelligence, most of the people in this room know what that means. What it means for me is it's really about that juxtaposition of AI techniques and machine learning from a software perspective, but also how does that work in terms of either bio-inspired or implementing bio-inspired computational techniques in hardware, and then how does that link with that software to solve engineering problems. Now, I come from a design automation background, but in many cases what I've actually done applies into real applications, whether that's robotics, actuators, various aspects of electronic design. So what I'm going to do is sort of take you through a little bit of each of those elements and how I've used those in various teams to solve engineering problems. So we're going to start with a bit of an introduction to where I'm coming from computational intelligence, and looking at the talks today, I think there's bits and pieces across that whole spectrum, which is great. How you deploy it in platforms, how do you actually implement it, giving some examples, and then some Q&A. So computational intelligence is an interesting term. We hear a lot about machine learning and artificial intelligence. Computational intelligence is essentially a subset of that. And it's much more about that interface to hard computing. So it's much more about solving real problems, doing hard computation, but also some of those adaptive soft computational techniques. Includes lots of things like optimization, several talks on optimization today, neural networks, decision making, etc. One of the things that I've often heard, and I'm sure we've all heard this as a community, is that we don't need this AI nonsense. We're engineers, we can come up with the equations, we can solve the problem. Why do we need all this weird stuff? It's a really interesting conversation with Manoush and Charles earlier about how good is good enough. And I think, Charles, you said it really nicely with a lot of nines. So 99.999%. I think Manoush said 99% is not good enough. And that's a really perceptive comment, because where do we draw that decision-making line? When is good enough? And so I think my perspective on this is that in most cases we need to try and identify where computers can do what they're good at and we can do what we're good at as humans, and try and identify where that interface is. I think one of the counter-arguments to the counter-argument is that that's probably true in a lot of engineering. We've been doing engineering a while. We know the fundamentals, we know the principles, we know a lot of the equations, and that's really good. But when it gets really complicated, and when there are a multiplicity of design factors, or the environment is constantly changing, and we need to adapt to new situations, then it becomes incredibly hard, incredibly time-consuming, with a lot of computational energy required. And that's when adaptive systems, machine learning, computational intelligence can begin to really pay off. And I think from an engineering design perspective, it's not about designing a circuit where it's a topology that we know anymore. It's much more creative than that. It's dealing with unknowns, perhaps where we don't have analytical or empirical data. We need new approaches. So that's where computational intelligence comes in. Machine learning, it's kind of useful to think of this or define the term, because I think it's misused. I think machine learning and AI are often kind of smeared into the same term by people who don't really know what they mean, but it's a subset of AI. And I think it's quite useful to clarify what the definition is. It's where we use algorithms to improve the performance of computing. I think this is a critical point. It's not just some magic silver bullet to solve these problems. It's about getting better performance, and it's using learning to help us with that. So as engineers, or as an engineer, I think it's much more about less some esoteric ideas about what is possible. That's very nice, but I want to solve problems, I want to do it efficiently. So that's where I think machine learning wins for me. So computational approaches. There's a really good book. I used to teach this topic, so it's a really nice, broad textbook, goes into some depth, Eberhardt and Shi. So if you wanted to dig into that, particularly the students in the room, it's a really good place to start, covers a lot of ground, so very well worth a look. So for me, these are the sort of key techniques, and there's different types of techniques. So we've got optimization, so things like genetic algorithms, evolutionary algorithms, artificial neural networks of various kinds, different types of machine learning, classification. There's a whole tranche of Bayesian stochastic probabilistic techniques. This is probably the poor relation, I think. There's a lot of work. We're talking about data, we're talking about uncertainty, and I don't think we spend enough time as a community really understanding this and building this knowledge and depth of understanding into what we do. It's absolutely crucial. And then you've got the fairly old techniques like fuzzy logic, but I've sort of lumped it under the term imprecise definitions. So that poor data, limited data, I think is really important. So what do we do when we've got a lot of variability? What do we do when it's incomplete and imperfect? I think those are critical things to understand. If we do that, then we can do much better with the interpretation of the algorithms. My personal favorite, which is something I came across by accident in my PhD, is genetic algorithms, where I think it covers a lot of these areas. There's classification, there's optimization, there's also the issue of multiple data sets, so big data sets exploring a design space. And this is why I got into this, was thinking about exploring large data sets where there's big gaps, big holes, inconsistencies. How do you navigate that so that you can identify where the best solution might be? And in fact, one of the nice ideas that came out of the work I was doing with other people too was the idea of not just hanging your hat on one particular technique, but thinking about, well, what if you can navigate a big design space, then come up with a few candidates, and then switch to a more perhaps forensic, direct approach of optimization, so you get the best of both worlds. So I think it's a really great technique, all about creating large data sets, evaluating, ranking, doing some statistics to do crossovers and mutation, and then ranking again and just repeating. So that's how the algorithm works. But there are issues. Again, it's not a silver bullet. Very often when you look at GA, so genetic algorithm work that's published, you can see that you get so far, and then it kind of just plateaus. And that's because the researchers in question have just hung their hat on that one technique, and it runs out of steam, and you need to adapt, change to a different technique, try a different outcome. And you can get stagnation. One of the issues with any optimization, as most of us who've done optimization will have come across at some point or other, is false peaks, or you end up stuck in a trough and you can't get out of there. So stagnation is definitely a possibility. And it's a big issue when you're looking at adaptive systems or working with big design spaces where you may not know it's stagnating, but you're stuck. And you need to think about how to get out of that. One of the other nice things that I really like about things like GAs is the code is so simple. I put some pseudocode. Actually, you could write the code in Python or C with not many more lines than this and do a basic genetic algorithm. So it's really simple to code, which means that you can do very compact coding, very efficient coding. But the key there is making sure that you've got really good data analytics, good data sets, good quality of data, and you don't make bad assumptions. So yes, it's very easy to create a population of candidate solutions, but they have to be the right candidates. You have to have the right parameters. The assumptions you make have to be intelligent. So it's not just about writing good code. The code is easy. What's hard is setting the right assumptions, setting the right evaluation function. So how do you establish the fitness of a candidate solution? How do you do that correctly? Do you do multiple parameters and do some kind of weighting function? And if so, how do you weight it? How do you prioritize it? So you have the issue of building in bias when you do this kind of optimization or classification. It applies to all computational intelligence algorithms, but in particular where you've got large data sets. So at every step of the way, it's simple to do, but there are pitfalls all the way through. Linking this is things like artificial neural networks. So you've got techniques such as GAs or other optimizations, steepest descent, etc., simulated annealing for optimization. But neural networks are all about classifying. And the root of most of these neural networks has come from an attempt to mimic biological behavior. You look at things like the Spinnaker project at Manchester with Steve Ferber, where it's about having massively parallel computation to model biologically semi-realistic, you would say, neural models, more on that in a second, but on a massive scale. So looking at billions of neurons to try and come up with something that approximates or mimics the function of a brain type structure. So whether that's in a mammalian brain or a human brain. And again, the process is very simple. You have an input, you have an output, and you have a very simple network, essentially, structurally, that is searching training data and labeling it. It's doing a basic classification. But the whole point here is that it's trying to mimic biological behavior. It's one of the one of the first bio-inspired computational techniques. And that has pluses and minuses. So the brain is very good. It's also very slow. It's massively parallel, but it runs at about kilohertz. If you think about it in computational terms, it runs very slowly, but with a lot in parallel. It also has very good resilience and very good adaptability, but it's not perfect. So going back to what I said before, computers do computation very fast. We're quite slow, but we can deal with lots of sensory inputs in parallel very efficiently. And we have evolution over many generations of us as organisms, plus we learn by being constantly sensory stimulated as we grow. So the challenge for artificial neural networks is, again, not the topology. That's fairly straightforward, a network of neurons. But how do you find the connection weights? I remember working with neuroscientists when I first got into this. And we were looking at very simple animals. First of all, looking at something called C. elegans, a little nematode worm that had a very well-defined neuron structure. I can't remember how many neurons, about 200, 208, something like that. And I said to the neuroscientist who'd been working this in his whole career, I said, how are they connected? And he says, I don't know. Okay, so after a while, a few breakthroughs later, we know how it's wired up. Fantastic. What are the weights? Don't know. And this is with a worm that can go forward and back and curl both ways, and that was about it. And even then, no idea. So the challenge for us as engineers is, well, we've got a rough map, but we've no idea how far apart essentially all the nodes are, the weights. We've got to try and figure that out. So in terms of trying to understand that, a lot of work has been put into modeling the neuron behavior. So you can model the network of the weights, but what about the nodes? Maybe we need to do more complex models. So there's a spectrum of models, all the way from very simple binary models, ones and zeros, with something called a perceptron. So most of us who've been doing AI will have come across a perceptron, so basically a threshold detector, all the way to, try not to fall off the stage, more biophysical kinetic models, which are based on the electrochemistry of a neuron, with the inevitable trade-off. Over at this end, very fast, very simple, great, they're binary, great for adapting to digital computing. Over here, with the kinetic models, biophysical, very slow differential equations, very slow to solve. So you're not going to be able to do billions of neurons with these models. It's just infeasible. And even if you could, what information do you get? So in practice, when we're trying to do this for real, we tend to sit around here. So something between maybe something called the Izhikevich model, which is a bit more complex than a binary model, but not as detailed as a full biophysical. So it has some nonlinearities with a few parameters. Maybe an integrate and fire, which has got a simple integration and then a trigger. So it's very digital in nature. And a lot of the work in, say, like the Spinnaker project tended to work at this level. with state-based or integrated fire models, maybe verging over to Izhikevich, but definitely at this end of the spectrum to get much more computational efficiency, to do things pragmatically. So implementing neural networks in practice, so we can make a decision about the neuron model, we can try and do our best to optimize the weights, and actually this is where tools like the genetic algorithm can come in handy, because they're very good at navigating big design spaces to try and optimize the functionality. And the neural network has got a very big design space with pretty limited data. Yeah. So quite often we use tools like the GA to help us optimize the parameters of a neural network of very large design spaces, lots of parameters, lots of connection weights to try and mimic the behavior that we see. In terms of modeling that behavior, we also need to figure out how many layers of these neurons we need. So if you look at a neural network, it's not just a splodge of nodes with connections. It's defined in layers from input through to output. And depending on how many layers you've got, single, 2-layer, 3-layer, and onward, will dictate how complex a solution you can analyze. So if you have a single layer, then pretty much it's like an exclusive OR gate. You can do single plane classification. So if you've got clusters of data here and clusters of data there, a single layer can find the line and you can discriminate the two. So fairly basic. When you get into 2-layer, then you can look at regions. 3 layers, you're starting to look at arbitrary complexity of regions and boundaries. So you're able to do a bit more subtle differentiation. In fact, this 3-layer model is all you really need for the majority of engineering or classification type problems. So this is helpful because it allows us to do very parallel type architectures with limited numbers of layers. Has been some work done in extending to look at more layers and having a deeper model, but theoretically and in most practical cases, 3 layers are sufficient for the vast majority of engineering problems. So that's fine. So we've done optimization, we've now got our network. How do we learn? How does that happen? Well, this is where we need to take our neural network and we need to train it. So this is where identifying the parameters of a network come in. And we need to have different types of data sets. We need to be able to look at the outputs and assess how well they work. And we need training data and unsupervised training data with some kind of goal. And going back to what I said originally, the goal is critical. So whatever kind of objective function we use for optimization equally applies to machine learning. We could have a really good learning approach and it's missing the target. It's looking for the wrong thing. So we have to be very precise about how we define what this goal is. Now, when I say precise, I don't mean that it has to be a precise answer. What I mean is we have to be absolutely clear about what that goal is. The goal itself may be very adaptive or very flexible or quite broad, but that has to be defined. Okay. Different types of machine learning. Supervised, where we're learning from very clear data sets with labeled input-output pairs. Unsupervised learning, really interesting. I think a lot of potential here where we have unlabeled data sets and we're just looking for patterns. We're looking to explore the design space. As a design automation person looking to understand and create new topologies of design or new types of design architecture, this kind of unsupervised learning is really interesting. But it's also a bit of a crapshoot. You know, you don't know what you're going to get necessarily, and you're going to run a lot of iterations hoping that you find something interesting, and then you've got to interpret it. Reinforcement learning is a really nice approach where you're using intelligent agents with a reward mechanism. So you're giving that positive feedback when you get good outcomes. So this could be applied particularly at something between unsupervised and reinforcement learning to just look in a design space and then give a little bit of reward when you see something interesting. So that's the theory and the architecture. How do we do it in practice? So we could write some code. bet most of us in this room, if not all in this room, have been writing code for one or all of these different sectors of computational intelligence. Lots of different platforms, from low-level coding all the way through to sort of more scripting type languages, sort of hybrid languages like Julia, which are building on Python or C++, which are quite nice. Lots of libraries and techniques already built in. And there are others, of course, but I think the point here is that it really doesn't matter. There's plenty of libraries now. There's lots of interfaces. We may have a hybrid solution that uses bits and pieces of compiled libraries where they exist. And also, I think it depends on the computational platform. So if we've got maybe a really nice graph core chip that's got some built-in machine learning that we can take advantage of, well, yeah, let's use it. We may only have small embedded processors. OK, that's fine, but we need to be very optimized and focused. Python is great from getting started as a perspective. It's got loads of libraries, open source. So as an academic, it's a great place to start. As a PhD student, great place to start. And the performance is probably good enough for a lot of applications. Jupyter Notebooks, of course, it's a little bit suboptimal performance-wise, but a great way to share information. But there's also other aspects of both Python and notebooks which are really useful, which is being able to deploy onto a cloud. So last year I was doing a bit of work with Red Hat on how you can create virtual machines and then setting up not just the code, but also the environment, so that when you want to deploy it or share it, you're not just giving somebody code and then they have to spend 2 weeks trying to figure out how it all works and where all the libraries are. You're giving the whole infrastructure. But there's another benefit to that, which is that when you do that, and you have this self-contained environment, and you take the time and trouble to do that, you can deploy it into, say, a cloud or a server application where you've got everything ready to go, and it becomes not just a piece of code anymore, it becomes a true data science environment. And this is great because this allows you to deploy it to different platforms, but also look at high-performance computing. You deploy the code with all the libraries and any data setups in a container. You've got all of your setup included as part of that, and you can share it or you can upload it to, say, something like Red Hat or AWS or Azure to give you a really powerful cloud-based processing environment. So it's really useful both for sharing amongst other academics and teams, but also to take advantage of high-performance computation. So just to finish off, some practical real-world applications of computational intelligence in engineering. So I'm a sort of power electronics and electronics person, so that's kind of the bias of where I've been looking at using these. So a really nice paper by a team from Aalborg. So this was focused on power electronics, so it's nice to see how this sort of more computer sciencey application is moving into sort of very hardcore electronics and engineering applications, and the same throughout the various fields that we've got in the room. This was a piece of work done with battery characterization for electric vehicles. And the interesting thing here is that previous work had tended to look at individual cell characterization. This was looking at whole vehicle simulation, where there was no access to the individual thousands of cells, and it was being able to discriminate features from incredibly noisy data with very limited metrics or measurements, empirical data, just top-level data, but still being able to characterize the overall system behavior using evolutionary algorithms and neural networks to classify and to identify those nuanced features and looking at it statistically over multiple runs. So really powerful. And also looking at doing system exploration and design. So then looking at whole system optimization with large data sets in multi-dimensions and multi-disciplines, and then being able to optimize key design parameters. So this was really looking at my field, which was design exploration. So one of the things that, another piece of work that identified here was looking at machine learning really from a classification approach. And what was really interesting about this was looking at the relationship not just of the identification for a specific example, but looking at long-term lifetime reliability of the models. So I think this plays to the conversation earlier about the 99+%, which is not just looking at that one point in time, but looking ahead to the longevity of the stochastic aspects of the data set that we'd identified. So this is another nice piece of work that was presented last year at APEC 23, which was really interesting because it was looking at very large data sets, looking at this stochastic aspect for clustering and identification. So, in summary, looking at the agenda today, I think we're covering so many aspects of AI and engineering. It's really exciting. And I think computational intelligence, which is where I'm at, which is kind of at the building block level, has so many of these fundamental techniques, and I think there's huge potential in growth, especially in machine learning. So I'm really excited to hear what the rest of the day has to offer. With that, I'll say thank you very much.
Thank you, Peter. So if we could go to some questions from the room now. Fantastic, yep.
Yeah, thank you for the presentation. Interesting,
Thank you.
covering a lot of topics.
Yeah.
I've got a few questions. I don't know how much time we got, but the first one. In classical optimization, there is something called curse of dimensionality.
Mm-hmm.
Now, you mentioned genetic algorithm, and they're very good in identifying a global optimum. But if you want to get the right answer and you want to use it with high fidelity simulation, it becomes really expensive. So how do you cope with that curse of dimensionality? And what's the biggest number of design parameters that actually Dyson uses in a real application?
Oh, right, so I'll unpack that. So the last question, I can't answer that for various reasons. No, it's really interesting. So there is a trade-off. So what I found with the GAs, the genetic algorithms, is exploring a really large design space, thousands of parameters, sometimes even hundreds of thousands of parameters. Something like an IC design, integrated circuit design, where you have millions of transistors and trying to optimize those. That's the kind of challenge we used for that. And it's pretty effective. The key is not being too tight with the constraints. So you have quite a loose constraint set. You don't worry too much about trying to tighten it down too much. You kind of have a fairly loose definition of your objective function, and you look for clustered, broad clusters, candidate areas. And then very often, you switch, as you were alluding to, you switch to a different technique, but you focus on that smaller design space. So you kind of have a hybrid approach, at least that was my experience. And it kind of came by accident because I was writing some software tools with a variety of optimization techniques, and I was comparing them with the same problem. And then I accidentally ran an optimization with the GA and then pressed the wrong button, and it ran some simulated annealing, and I went, whoa, this is really fantastic. And what happened was it had found a cluster of candidate solutions, ditched the rest, and then it was doing the simulated annealing, so fairly old-fashioned technique, but working in a very constrained data set, relatively, in a good candidate area, and then it was able to really go much deeper. So that kind of hybrid approach has become quite common, and I think that's a good approach.
You talk about gradient-based method, you don't use that?
You can use that, but I've found those to be not as efficient as things like simulated annealing. I mean, simulated annealing is it is essentially gradient-based approach by another name. There's a randomness to it, but it does have that thermal decay aspect. But you can use the steepest descent. But any of those traditional techniques will work once you've constrained the space into something where you've got a good set of candidates. It can save you a lot of time.
Fantastic. I think we've got enough time for one more question. I've got one if the audience don't.
Yeah.
So from the perspective of sort of environmental impact of AI, can you see how sort of generated concepts within power electronics can compete sort of environmentally on CO2 production with those that are manually engineered?
Well, there's two aspects to that, and one is you can, because what you end up with is much more efficient system. So from a power electronics area, the reason for doing it is to get efficiency way up, which means that losses are way down, which means that energy requirements are reduced. And if you look at the UK energy requirements, electricity requirements, our consumption is going down as a nation because we're becoming more efficient because of better power electronics, and it's partly because of this. Not just because of this, but partly. So better design. So that's one aspect. There is a price to pay. And this goes back to your point, actually, which is that if you just chuck it at data centers, get big problems and chuck it at data centers, that costs money and it costs power. One of the biggest growth areas in power is in data centers. So it's very tempting to take a big AI problem, chuck it as some cloud server and think that it's free and it costs no power. And in fact, it's become an increasingly high proportion of our global power demand is in using machine learning and AI. So each time we use Google or Bing or whatever it might be, or ChatGPT to ask something, it costs power. It's not free. Even something as humble as an email costs power. So every time we use the cloud or infrastructure to solve a problem, there is a price to pay.
Thank you very much, Peter.
Okay, thank you.
So next up, we have Michael Groom from the University of Oxford. He is talking about safety for mobile manipulation for domestic robots. Thank you very much.
Thank you. So hi everyone, my name is Michael Groom. I'm a first-year PhD student in the Cognitive Robotics group, which is led by Professor Lars Kunz, who's sat on the back row there within the Oxford Robotics Institute. So I'm lucky enough to have my studentship funded by Dyson, my IK studentship, and also to have the opportunity today to tell you a bit about my work, which is all centered around safety for mobile manipulation for domestic robots. So I believe that domestic robots have the potential to increase the quality of life for a large number of people, but obviously to do so, they need to be safe. So robots, they operate with uncertain observations, they perform actions that have stochastic outcomes, and they'll do all this in open-ended environments, which combined together makes safety quite challenging. I hope everyone here agrees with me when I say that robots need to be safe. Probably the easiest option to make them safe was to probably just don't try many actions at all, but a robot that does nothing is a pretty terrible robot. So we need to kind of come up with ways that we can maintain the utilization rate and the task success rate of these robots while being robust to these sources of uncertainty. So this presentation is going to kind of highlight some of the work from the first 8 months of my PhD, and then briefly at the end outline some future research directions that I think are quite interesting. So this piece of work was the first piece of work that I've been involved in during my PhD. It's led by another student in the Cognitive Robotics group called Ricardo Canizaro. It's titled Physics-Based Causal Reasoning for Safe and Robust Next Best Action Selection in Robot Manipulation Tasks. A bit of a long title, but we submitted to AROS this year, so under review at the moment, so fingers crossed. Available on archive as well, so if anyone wants to check it out, please go ahead. So kind of the motivation for this work is safe and efficient robot manipulation. So I guess in this context, a domestic robot kind of interacting with objects in a household environment. It's a big prerequisite for a lot of tasks that you might want a domestic robot to perform. As kind of briefly discussed before, we have to deal with perception and actuation uncertainties. So to address this, we proposed a physics-based causal reasoning framework for modeling the semantics and uncertainties of the robot manipulation task and decision-making process. So in the paper, we primarily focus on a block stacking problem. So it's a pretty simple problem. It's just task is to stack blocks consecutively while keeping the tower stable. I guess on the surface it seems quite an easy problem, but you deal with a lot of the problems we mentioned before, so stochastic actions and partially observable outcomes, which make it quite tricky. So the proposed framework kind of solves two subtasks related to this problem: stability prediction of the tower and next best action selection, so where to place the next block on the tower. So our approach formulates the problem as a causal Bayesian network, which describes the robot's decision-making process and the system dynamics probabilistically. So I guess it's kind of a little bit small here, but we start with an initial true tower state, S0, which we take an observation just through perception, so for cameras. That has perception noise, which we model in our system just as some noise distribution, additive noise, that we can parameterize. From that observation, we decide a next best action to take. When we take that action is going to suffer from actuation uncertainties from the robot, which again we parameterize by some noise distribution. Once we take that action, it updates the tower state to the next state, and the graph continues and continues, and hopefully by the end of it, you end up with a tower that's stable, and you've completed your task. So to model the transition dynamics on that graph, we use a physics-based simulation, which accounts for the perception and actuation uncertainties. So by combining the simulation and the Bayesian network, we define a causal generative model, which we can perform Monte Carlo sampling of candidate actions to obtain tower stability probabilities. And once we have tower stability probabilities, we can select the next best action to take. It's conditioned on the observation of the tower and also how we parameterize the perception and actuation uncertainties. So this is a video from a lot of the slides the same here. I was hoping it's just cropped on the end. There's a video of the robot working, performing this task. So it'll get to it eventually, hopefully. But the video just shows our method being deployed on the Toyota human support robot, which hopefully we'll get to. Here we go. This is in simulation. And we also actually deploy on the real robot in the lab, which is quite fun. So one kind of good advantage of this method is it's deployed online, so it can kind of actively recover from previous actuation errors that it's made. So you can see it places the first block, it's slightly off-center, probably a bit towards the camera, and then the next action it takes kind of hopefully corrects a little bit and places it further back to where the true kind of stable location would be. So that's kind of the first 6 months of my PhD, probably. Recently, I've been working towards future work. So future work will hopefully continue to improve the safety of manipulation policies. Most recently, I've kind of been viewing safety as the avoidance of unreasonable risk. So that kind of definition leads quite naturally to the idea, can we give a robot the capability to quantitatively reason about the risk of taking actions, and then only take actions that kind of don't have that level of unreasonable risk. So this is a paper from Lucas Schneider et al. At ETH Zurich. It's a really cool paper. I'd encourage people to check it out. It's titled Learning Risk-Aware Quadrupedal Locomotion Using Distributional Reinforcement Learning. So this paper, they use a distributional actor-critic reinforcement learning approach. So instead of relying on an expected value of a state-action pair, they predict probability distributions of the state action pairs that hopefully kind of, with the learning process, kind of encode some of the uncertainty of taking specific actions given a robot state. So once you have this probability distribution that kind of encodes the uncertainty of the value of taking an action, they apply risk metrics that consume the value distribution and produce a risk-sensitive value estimate. Now this allows them to train a policy where they can do locomotion with the robot, but also have it kind of dynamically adjust to how sensitive to risk they'd like it to be. So at the top here, there's more risk-affine approaches where it will just go for it, and then more risk-averse approaches where it's a bit more conservative in the actions it takes, trying to maintain the kind of task success. It's quite a cool approach because it kind of allows them to adjust on the fly during deployment the kind of acceptable risk levels. Obviously, my talk's about manipulation, and this isn't manipulation. So kind of future work is kind of looking at trying to train a similar approach or similar policy to apply it to manipulation tasks using mobile manipulators like the HSR on the left. I think I've probably kind of run out of time here, so I'll probably wrap it up. So yeah, if anyone wants to get in touch, there's my email, and please ask some questions if anyone's got any. Thank you.
Thank you, Michael. Do we have lots of questions from the room? At the back.
So your model, stacking, does it always go forwards, or can it move the block to make it more stable before putting the next one?
Sorry, can you repeat that? I can't.
So your model, you put the one block on, and then the next block is a little bit off, and then it balances the next block to lean further.
Yeah.
Can the model just put the second block in a better place when it realizes that it's not balancing well?
So the idea with the model is it kind of, you ideally want to put it in the perfect location every time, but there are, especially when you're using mobile robots like the HSR, there are a lot of kind of uncertainties, and you think you've moved to the perfect place, but in reality, you haven't. So this kind of approach, it lets you deal with the kind of stochastic outcomes and realign to place it at the next best action location. Yeah.
There's never a time when it just will replace the second block in a better place.
No, not in this approach, but yeah.
One quick, very quick.
Yeah, sorry. I missed the physics side of your approach. Is it learning from what we just, like a previous question, from what's happening and correcting itself? Or actually you know, from the previous pictures, you just compute center of gravity and the moment, and you try to balance it mathematically? That's, for me, that's like a physics of gravity.
So in this kind of graph, this is like the physics simulation that we use. So we observe the initial tower state and then check potential candidate locations that are kind of randomly sampled based on the noise distributions that we define.
Yeah.
So we say we want to place it at this spot, but there's noise on top, additive noise on top of that. So it's kind of fixed around that spot, but random. You perform Monte Carlo sampling on that to get a tower stability.
But the bottom line for me is, are you solving any equations in terms of in your training as you go forward for the robot? You're not.
We're just running the simulation and kind of in the robot's head, and then it'll decide what to do.
Just learn from what's observing.
Yeah. So the way we parameterize the noise, you could learn that. So in the paper, we perform a bunch of simulations to kind of understand the perception uncertainties we see, and also the actuation noises we see in 3 dimensions as well. Yeah.
Okay.
Thank you very much, Michael.
Thank you.
So next up we have Edward Stowe from Imperial College London talking on using tensor contractions to bring automatic data layout optimization to robotics. Thank you.
Hey everyone, thank you for inviting me to this talk so I can talk to you about compilers and things. A bit different from robotics, but I promise it's related. This talk is really about how we can raise the abstraction level that we write code in so that we can gain lots of benefits from the compiler, we can increase portability, and overall what we can do is we can make the code we have to write by hand last more than one project lifecycle, so that one algorithm can be used over and over again in lots of different cases. So, for example, graph algorithms are everywhere, but we're going to look at Gaussian belief propagation. This is an algorithm people are starting to use more and more for robotics, for probabilistic inference over a bunch of measurements in the real world that are factors, and variables that we want to know about, and the factors describe measurements between them. So that all operates on a factor graph. And so when we think about programming this, traditionally, we think, well, we need variables, and we've got to have data for that. And we need edges, and we need to have data for that. And we've got factors, measurements, we need to have data for that. And we put that all into a graph data structure. And then we can think, great, now I need to do my algorithm. So I'm going to take every variable, and I'm going to sum across all the incoming edges, pull that information out, I'm going to do some work on it, some computation, and then push that back to the edges. And then I'm going to go through my factors. And we're going to take all that information in from the edges, the messages from the variables to the factors, and perform marginalization over a bunch of Gaussian variables so that we can optimize for the most likely state of those variables. And then I'm going to push that information back out through the edges, back to the variables. But the problem with this is that it makes sense, and it's how the papers are written, but it bakes in this node-centric view of the computation. And that node-centric view isn't always optimal. It's dependent on the program, it's dependent on the context, the situation, the size of the graph, the hardware you're running on. And all these things, they mean that if you want to deploy this algorithm in several places, now you've got to rewrite your code. Or you might have to think about different assumptions that you've accidentally made while doing it. So on the left here, we see this sort of baked-in representation at the bottom here has the little arrows that jump between the nodes. And that all exists only because of the way we wrote the program. Whereas on the right, what we can see is by using tensors as the language to talk about the program, talk about the algorithm, all we have to do is have our A, which is an adjacency matrix, which represents all the edges. And by multiplying, or doing a matrix multiply, effectively, with A, we can take variable data and push it out to the factors. We can do the computation on it, and we can use A again in the next line to push it to, push it back to the variables. And then we can do our little marginalization step, sort of still per node, But that inside that foo, we can have more tensor logic, right? So that doesn't necessarily have to be written as node-centric when we actually come to compile this. And what this does is it means we have no more explicit loops in our code, so that we don't have to optimize loops with loop tiling and vectorization. All those things that we might do manually can all be done automatically. There's less manual optimization needed. Yeah, and those assumptions about how it's performed, the sort of strict, well, we do all these loops and then we do all these loops is gone, which allows the compiler lots of freedom to just say, well, we've got our concept of what information is moving, but we don't need to care about the data and how that's represented yet. And so the compiler can optimize that however it likes for different platforms. And so what the point I'm trying to make really is that the tensors are more portable. So you can take a laptop, you can take a cloud-based system, a phone, a robot that's this big, and a robot that's this big, GPUs and accelerators and all these things. And if we can write the algorithm once, then we can just choose and we can search that design space of robots and applications and hardware without all the manual effort of rewriting and repurposing and optimizing by hand our nice, perfect algorithm for all these different situations. It also means that the same code you write can be used in the future. So as compilers get better, as new accelerators come out, you don't need to, again, rewrite everything. And then so the work I was focusing on mainly is about how we optimize the data layout. So here we show a big graph or a big tree. And that's what, to me, data layout looks like. You sort of have a structure. You've got dense arrays. You've got mappings from different indices. You've got all different complex things. At the end of the day, this is basically just representing that you've got a few arrays. But there are so many different ways to store that data on hardware that the compiler is going to be able to choose between a whole huge design space of these different options, whereas we as programmers aren't. And if we try, we just end up writing bugs. And we end up updating this bit of code and not that bit of code, and then it's all slow, and you can't think about the whole program as one. Whereas a compiler in a well-designed technology, you can have all these different options, and the compiler can decide and optimize across multiple different iteration calls for different hardware targets without people having to do as much work. So where it's going to is in the future, we want to have sort of a graph of different components. And so the compiler technology really is the key to how we take high-level design concepts like PDEs or graph algorithms or GBP, and we go through different sort of understandings and we optimize different parts so that we can get down to a simpler and lower level system that then can target lots of different hardware. So thank you for listening, and if you've got any questions, I'm happy to answer.
Fantastic. Any questions from the room? Okay. I'm wondering how this works with moving to a new hardware platform. Do you have to have a really good idea of what your hardware platform is going to look like and actuate like? Or can you sort of use the generative nature of this to sort of access some of those actuators and sensors you have available?
So the beauty about trying to have if we go back to this one, have a sort of collection of different hardware compiler technology tools is that you already have buy-in from a lot of hardware vendors that they say, well, they want to be able to optimize and make their hardware really good at machine learning, which means at some level they're doing something that looks like tensor contractions and tensor logic and stuff to do machine learning or deep learning, whatever. So we want to say, well, let's repurpose that. If one of these boxes inside of the compiler is a representation of tensor logic for machine learning, and we can take graphs and turn that into tensors, then we can leverage all the hard work the hardware vendors are doing to make that really fast without having to rewrite it all ourselves in our own special graph algorithm version of it. So yeah, we get that leverage ability for the vendors want to make good compilers for their hardware, and so we just have to be able to plug into them rather than rewriting it ourselves.
Okay, fantastic. Thank you very much. Oh, we've got a question. Ah, yes, fantastic.
I probably have a very basic and similar question. It's basically, I wonder how practical it is. What kind of hardware requirement do we need, and what is the stage of development so far you have in terms of open sourcing, for example? Is that available to be used, for example? Yeah.
So in terms of requirements of the hardware, I mean, I've written a sort of, a version that just works on Python, right? you can, if you wanted a slow compiler, we can compile it to native Python. It'll run slowly, but the hardware there are no real hardware requirements other than that someone's written a compiler that converts from some language to it. As far as what we've made so far and developed, we have a domain-specific language that talks about tensor contractions. And then we've converted that into, we have a pipeline that takes that into this data layout idea, and so a domain-specific language that talks about data layout. And then from there, we use things inside of MLIR as a tool, as a compiler toolkit framework, to then go all the way down to x86 or anything else that's supported by Clang, effectively. So we've got a decent spread. We've also got, from MLIR world, you can go into GPUs and all that sort of stuff that's not tested. But we have basically, by using ecosystems of compiler toolkits like MLIR and these other project XDSL, we can get a lot of different backends without having to do the work ourselves. We only have to talk about that sort of high-level to mid-level representation.
Thank you. Fantastic. Thank you very much, Edward. So just before our next talk, a couple of housekeeping things. Those of you who are joining online, do feel free to pop your questions in the chat that we have on YouTube. We'll try and get some of those questions to our speakers. And also a reminder that photography in this room, absolutely fine, but photography outside of this building is prohibited, so please don't take any sneaky pictures. Fantastic. So next up, we have Vasil Atanasov from the University of Oxford on unsupervised skill discovery for legged robots. Thank you.
Hey everyone, my name is Vasil, and I'm a first-year PhD student at the University of Oxford, and I'm working on a Dyson studentship. Today I'm going to talk about some of our work on unsupervised skill discovery that I did over the past few months. So first of all, why do we actually care about unsupervised skill discovery? Well, there's a lot of different tasks that we want to do with quadruped robots, and at least with reinforcement learning, the current approach is to come up with a new set of rewards every single time, tune those rewards, and then train a new policy from scratch. So sometimes you might have to add some task-specific inductive bias, especially for more complex tasks, which then really slows down the process and doesn't really scale well when you want to do maybe 100 different tasks. It would be very nice if you can somehow learn a big set of skills or behaviors that we can, in a mostly unsupervised way, without having to manually specify rewards. We could then use those skills for different downstream tasks simply by fine-tuning a policy, which takes a lot less time. So this is kind of what we were trying to do with our work. And what we ended up doing was that we introduced an unsupervised skill discovery method for learning different locomotion skills on quadruped robots. And we acquired these skills with only an intrinsic diversity reward and some regularization terms, so nothing task-specific. We proposed a constrained skill matching objective that, compared to the other baseline methods in literature, achieved a much more uniform and richer coverage of the state space of the robot. And then that allowed us to also do zero-shot go tracking, so track different desired base positions on the real robot without having to specify any task rewards and without any further training. So just as a bit of background on how unsupervised skill discovery usually works, is that we have this skill condition policy pi that can generate different trajectories depending on some conditioning variable z, which we call the skill. In order to actually train this policy, we use a mutual information objective that comes from information theory. And the idea behind it is that it's a measure of how much information we gain about one random variable z, in this case the skills, simply by observing a different random variable s, in this case the states. When we maximize this mutual information objective, what we end up doing is essentially saying if we observe and know the trajectory the robot took, can we guess which skill it took in order to actually do it? So there's quite a lot of different ways in which you can optimize for this objective, but the approach we took samples an n-dimensional continuous vector as the skill, and then trains an encoder phi that takes real states and maps them to a latent space subject to a specific constraint. So I'm not going to go really into the maths and the details behind it. We can the way it works is that you sample a skill z from some prior distribution. You give it to your policy and you run it for a number of steps. And then you go from state S0 to state ST. You pass these through an encoder, which you can kind of view as a discriminator that tries to guess the value of your skill, just given those initial and final states. Then you can imagine that the more different your trajectories are, the easier it will be for this discriminator to actually guess the correct skill. To then train the actual policy, we use reinforcement learning, and then we give the agent an intrinsic reward based on how low the loss of that encoder is. So basically encourage the policy itself to produce more diverse trajectories. And then we combine that with some smoothness extrinsic rewards in order to actually be able to deploy that on the real robot. So what skills do we end up learning? Well, for two-dimensional skill spaces, all the skills that we do learn are different locomotive behaviors. And at test time, if we sample skills in the pattern you can see on the left, it results in the following Cartesian XY trajectories that you can see on the right. So for the baseline methods, different directions of the skill correspond to different directions in real space on the robot. However, regardless of the magnitude of the skill, all of the behaviors end up having the same velocity. Why this is a problem, you're going to see in a few slides. Compared to that, with our method, you get to preserve both the direction and the magnitude of the original skills, and then you learn a much more uniform distribution of motions where you can do standing, walking, and then running, depending on the magnitude of the skill. Then if we simply invert the problem and pick a desired base position, convert that to the latent space, and give it as the skill, we can actually do zero-shot go tracking, which looks like this. So as I mentioned earlier, in the baseline method, since the robot learns only a very narrow range of velocities, it tends to overshoot and then just orbit around the target without actually being able to stop. In contrast with our method, the robot can speed up and slow down depending on how close or far it is to the goal, and then eventually stop once it reaches it. So one of the limitations for two-dimensional skill spaces, at least, is that you can only control one small subset of the full robot state, which happens to be the base position. However, if we increase the dimensionality, for example, to 6 dimensions, we can actually retain more of the original information and get to control a bigger part of the state of the robot. For example, as you can see here, reach different positions also with a desired orientation. So in conclusion, our method can be a very powerful alternative to reward-dense methods because it can achieve very rich locomotive skills with just an intrinsic reward without any specific exploratory or task-based rewards. It's very scalable to higher dimensions, as you saw, which gives you more access and more control over the different dimensions of and states of the robot. And one of the directions that we're actually looking at for future work is not only doing locomotion, but actually loc manipulation. So moving the robot and also manipulating different objects, maybe with an arm on top or just with the legs of the robot itself. However, one of the caveats is that it is a bit harder to train as you have more and more skill dimensions. Finally, compared to the baseline methods, we achieve a much more uniform state space coverage, which then gives you much more fine control over your skills when deploying them on downstream tasks, as you saw in the previous slide. So yeah, that's all. Thank you for the attention. And here you can see a few videos of some of our hardware experiments on the Animal C robot. Do you have any questions?
Fantastic. Questions from the room? While you're thinking, I'll drop one. So I'm just interested to what resolution this is operating at. Is it actuator level, or do you have a layer of abstraction between that?
So we operate directly on joint positions. So there's like a low-level PD controller that gets torques out of those, but we just give it a desired position for each of the joints.
Fantastic. Any questions from the room?
Thanks for the presentation. It's really interesting. But I'm wondering how long does it, I assume that you don't train it in the real world, but train in a simulation. And how long did it take to train? And what do you think about the scalability when it goes up to state space like images? Or?
Yeah, so we train it in simulation in Isaac Sim, and it takes. So I train it for about 100,000 steps, which takes less than 3 hours. on like a standard RTX 3090 GPU. It converges a lot earlier, so you can probably stop it at maybe an hour and a half. So it really doesn't take long. In terms of scalability, so our method builds up on a different paper from last year. And in that paper, they actually showed that it can work quite well. A similar method can work quite well from pixels. So yeah, I think it's quite scalable to higher dimensions. But if you have some of that state information already, as we do on the legged robots, for example, it's probably worth training with the simplified state space.
Okay, fantastic. Well, with that then, thank you very much, Vasil.
Thank you.
And that brings us to our first break. So please get yourself a coffee. There's some juice on the counter with some water as well. The bathroom's just around the corner, but we'll be reconvening here at 11:45. Thank you very much.
Should I stay here? Should I stay here?
Hi everyone. We'll be kicking off the next session in the next minute or so. So if you could make your way back to your seats, we will get started. Yes, yes. You'll have your screen there. Okay. Yeah. Right, fantastic. So we're going to kick off the next session now, everybody. Again, another quick announcement. We're going to try and disseminate all of the slides from this session after the fact. But if you have any issue with your slides being shared by us, then please do come find myself, Mehdi, or Tanzi over here, or Jake at the back. Just let us know if we can't share your slides. For those of you interested in seeing the slides, I think we'll probably be sending it out via the mailing list that we've compiled from the attendance. So, with that over, we've got our next speaker here. We have Professor Manu Soleimani from Bath University, speaking on the application of AI in engineering and design, the opportunities in research and education. So I hand over to you.
Thank you very much, James. Okay, so let's start. So I was going to say a few words about the opportunity for AI for teaching and engineering, and also talking about examples of data-driven tools that I use for my research. So my research work is in the area of imaging, but more specifically on tomographic imaging. So when we can go through objects and find out what is inside of the objects. I was hoping to show a PDF file, which is hopefully the colleagues can help me to show a PDF file about a report on AI in engineering. Yeah? Yeah. Can you do that? Yeah. Because that makes my life a lot easier, yeah? And I come back to the presentation. Yeah, okay. So there's a report coming out of NSF on the kind of, if you like, marriage between AI and engineering. I think that's very useful. It will have a lot more useful information that I can give you, but we come back to that. So that's kind of, yeah. So the area is in tomographic imaging, and hopefully, well, I think you're all familiar with what the tomographic imaging is. The tools that are non-invasive and non-distractive, and so we can make a good, get a lot of information in the medical domain and other domains from these tools for from human body and in industrial applications and other applications. So the specific case for the use of machine learning tools is on inverse problem, which is you get information from the boundary of the object and you turn that to the image of cross-section and volume. And specifically, they can be categorized in different ways, but the easiest way to think about it is kind of, we have hard field imaging like X-ray, where the X-ray goes in a straight line. And then soft field is the ones that you have to solve some equations, and you cannot be described as a straight line. Okay, so electrical imaging, but on the other side is CT scan and so on. Okay, and then the old-fashioned tools. I think I will go between the old-fashioned tools and the new neural network-based tool, and so they're just examples of how they could be used and they perform differently. Okay, so for ray-based method, really for X-ray CT we can use ray-based method. Maybe we can use it for ultrasonic tomography, which I will also introduce in a second. So X-ray tomography is kind of absorption tomography. When you send a powerful X-ray from one side and you have detectors in the other sides, and you can reconstruct an image of absorption of X-ray in different parts. And actually the mathematical side of X-ray tomography is very well established. So generally you deal with a volumetric X-ray CT. It's called cone beam CT, which is a very efficient approach to produce volumetric image. And again, if you have full projection and all the angles and good data, then the mathematics of it is well established, fast, and very accurate. Okay, so that's where the software comes from, commercial machines that you buy. But actually, in reality, if you have missing data, and there's a good case for missing data for both medical applications and industrial applications, then those like pre-built, very fast real-time software is not going to do a very good job. So you have to go through some optimization, iterative algorithm to solve the problem. But this problem is kind of, if you like, the easiest way to describe is a linear, larger scale inverse problem, where you have noise in the data, but you can handle them quite well. So some ray tracing, and you can make a tool to create the forward operator matrix A, and then you can invert it. But the size of the problem is so big, you never make the matrix A because you cannot store them. So you just do it on fly. Okay. So really an optimization problem. We cannot really solve it as a least square problem. We have to add some extra terms, which we call it regularization terms. And so, and then you have sometimes parameters, single parameters or multiple parameters. Like, so in your imaging domain, you're dealing with very large data. For example, for X-ray CT, you're dealing with billions by billions matrix and lots of pixels and voxels. But there's a couple of parameters, a few parameters that will actually define the success of these iterative algorithms, which are supposed to be better than the traditional single line algorithm. So you can use, potentially you can use, as Peter presented today, for example, genetic algorithms just to optimize those parameters that are very critical, but yet just a few of them will have a role to play. So in my team, we develop an open source software that we call it, I call it Tiger, but the student that wrote it is Spanish, so he says Tigre, which is the same as Tiger. But it's basically a GPU-based toolbox that does this calculation. And a lot of iterative algorithm can be easily developed with lots of different types of CT scan data. But these are all using the old-fashioned methods, which can be programmed and used. So you can do it in Python or MATLAB or whatever. So this is kind of a list of algorithms that, so 5, 6, I don't know, 10 years ago, these algorithms would be like a state of the art and everybody would talk about them. The advance of GPU enabled us to be able to do these things in a reasonable time. So just to give a picture of dimension, in a medical application, we are looking at pictures of 512 by 512 by 512 voxels. In industrial application, this goes to like 4,000. So for medical application, for example, if you want to plan for lung cancer treatment and so on, you have about 10, 15 minutes to do this calculation. And at that time, I think before GPU, we were not able to do that. But now with the GPU and these kind of tools, you can actually do that. So that was before, if you like, the new techniques. But now with the new techniques, I think you can do a lot better. So an example of where these machine learning tools can be used, for example, to enhance in this case. So an application of X-ray CT, an industrial application, would be on metrology, so measuring dimensions of the objects, additive manufacturing objects, and so on. And you can see that with very standard convolutional neural network, you can learn to produce images as good quality as you would have all this projection data with a very few projection. So you can produce images that are as good quality as you would have had full projection data. So full projection means like the scanner goes around the body, in this case around the object. For human application, for medical application means instead of having like, let's say 500 angles of X-ray radiated to the body, have, let's say, can we have 40? And that in that case means lower dose and faster data collection. For industrial application, it actually means a lot faster data collection. So if you want to scan an object, additive manufacture object, you might go for hours and hours of data reading. Best not to do that. Do it a lot faster. So skip a lot of data and then try to compensate for that by computation. So computer will maybe take longer to analyze the data, but then you save time. Overall, you actually save time on use of machine versus the computer. Yeah. Do we have the slide to come back and? Yeah, please. So yeah, the things I was going to talk about the AI for engineering in terms of educational side. So I think if you have a look at this report that just came out recently from NSF about AI engineering, has got a very, very nice stories about where the AI they see as a tool for education. So the recommendation that you have to embed AI in all your undergraduate education and also produce master degrees and embed it in doctoral program. Of course, we have seen some PhD students that are focusing on that, but this is targeting on other types of engineers that are not engaging with these kind of activities. And then in terms of research, it lays out very nicely how it can help various types of disciplines with a different speed. I suppose if you're working in robotics engineering, then you're actually very close to this area, so you grab it much faster. But if you're working in a different area, then the time to get to this point could be slower. But I could argue that the potential is higher in an area that, I don't know, if you're optimizing a chemical process or something like that, and these tools are not being used as much, then I think the benefit can be potentially better. So I think I leave that for you to take a look at this report, and I think it will have a very nice read. Thank you very much. We go back to the slides. Yeah, so let's look at another application. So this is an ultrasound tomography, which we use it for an industrial application. So this is for carbon capture monitoring. So there was a method of actually converting carbon to some sort of usable material, and the tool that we were using was an ultrasound tomography. So X-ray, you send an X-ray in a straight line and you detect it. In ultrasound tomography is a bit different. You send the acoustic signal and you pick it up in the other side. And so again, unlike ultrasound scanners, the ultrasound tomography device will provide a cross-sectional image of the process. And yeah, if you use this kind of simple ray-based method, then you're cutting a lot of corners because you're simplifying a complex physics, which is going with acoustic propagation and so on. But you might be able to actually compensate for what you're doing in here, compensate it by adding some machine learnings at the end, at least in a supervised learning and so on. Yeah. So I'm going to skip these ones very fast and show an example of how this might work. So this is a very simple ray-based training data, so really purely computer-based. So connecting to a transmitter and receiver, intersect with pixels, and train that as to learn how we can produce an image of acoustic velocity or absorption. And the training is done only on a very, very bad computer simulation model. And then we applied that to a real experimental data. And also subsequently to actually real process data. And you can see that still detects all of these shapes. So some of these are due to the lack of data or insufficient amount of data. Is very challenging to do with the standard method, and the tool will pick that up. So that's a very good thing, because the training is entirely actually done very badly, because we are not modeling the physics of wave propagation inside of the domain and all these things. And then the testing is done on real data. So, well, if it works, we are hoping to do that for medical application. Again, this is a kind of supervised learning. So we have a kind of brain phantom. The sensors are attached so there's a variable ultrasound sensors. And here we can also see a CNN approach can overcome that problem. But the question is, can we take it a bit further and use it for actual medical application? If you can train it with some sort of computer modeling and then apply it to a real human, which very often we don't have the right baseline data, or is very expensive or costly to produce real data. Can we do that? I don't know the answer to that. But so we looked at the monitoring lung using again variable ultrasonic tomography. So we did some tests on the phantom. So we create something that looks like a 3D shape of a human chest, and we can see the in and out of the air inside of these balloons in here. And we took it a bit further, and we found some people to test on them, put the sensors around their chest. And it looks like we are able to produce cross-sectional image of human lung using that. So again, the question would be, can we apply the same method of doing some simulation-based, maybe simplified training, and then apply that to actually real human data, see if they're performing in a correct way. This is another imaging device which has actually been used in hospitals for intensive care units. It's called electrical impedance tomography. So it's one of those soft field tomography. So it's kind of, you have to solve the physics of electricity and then try to do the inverse problem of imaging the human lung, like again air in the lung. And it's been used, as I say, it can help you for finding information about regions of lung which is not ventilated, so you can design the ventilators to do it correct way. So this is a recent study that we try to create a kind of model that replicate what this electrical system is measuring. So we put electrodes around the body, we measure electricity, current, voltage from the sensors. But actually the function of human lung is different. So it's kind of mechanical things. You have pressure, you have air in and air out. So we create a kind of a twin model. So we took a lot of 4D CT scans. They provide dynamical picture of the breathing process from available data from the internet. And then we put them through a mechanical modeling, and then we created electrical modeling, which is our sensor is measuring this. And we combine these two together. So we kind of enabled our sensors now to have information from the mechanical modeling. Again, that seems to be working very well. Again, we left some of the patients out of that list, and the performance is very good. And here we actually applied to a patient or volunteer data where there's no training related to those people, and it still is performing very well. So I wouldn't call it like a identical twin, but there's some sort of twin relationship between a mechanical thing that is not measured by our sensor and an electrical system, and still there is good amount of learning from that process. Okay, so I think I'm going to skip those quickly. So this is another device which is magnetic inductive device. So this is an array of coil measuring the electrical metallic samples, and a couple of examples in the steel industry. So we put that around a steel billet to measure the solidification. And we did that actually in two ways. One is our device measuring an electrical conductivity, and the other one is a CFD modeling, which I'm not an expert. My colleagues did that on where the state of. So the question is to find the liquid phase inside of the steel billet as it solidifies. And we can see some correlation. So again, there's a good opportunity to try to twin this CFD modeling. Unfortunately, this CFD modeling took like 3 months to converge or something. So it's a bit slow process, but I think there's a good opportunity to do the twin modeling between these two different things. So one of them is modeling, the other one is observation, and try to help each other. Yeah, I think I don't want to go very slow. So basically, the other task was, again, going back to the same device, so magnetic inductive tomography. So you have very few sensors in here, 8 sensors. And normally you end up not being able to separate these objects from each other. So if you have 3 pieces of metal in here, so this is to detect multiple metal objects. And the idea was, can we use that for example, additive manufacturing? As we add parts of metal, can we like gradually build them to create a more complex shape? With our old-fashioned methods, there's no way we can detect any of these things because they are too close to each other and the number of measurement is very low. But this is supervised and kind of labeled learning, but not necessarily exactly the same samples. And it seems to be producing information that are otherwise almost like impossible to get from the old-fashioned method. So you have to solve a nonlinear, regularize, all this optimization that I was talking to you earlier on. All right, so yeah, and when it comes to the classification, the job is a bit easier because for imaging we have to find all the pixels and all the values. In here we have a liquid metal and we want to find void in them. And the task was to do the same measurement, but don't tell me where the void is. Just tell me if there's 1 void, 2 void, 3 void, 4 voids. And in that case, it works quite well. So I don't need to know where the void is, which makes life a lot easier. All right, thanks for your attention. And this was like very quickly going through the presentation. Thank you.
Fantastic, thank you, Manu. So, questions from the room, immediately.
Well, I can see similarity to what I will show later on. On the CT scan, I guess the real interest is detecting anomaly. And you talk about regularization and least square and data missing. How do you distinguish between the data missing and there's a problem that you need to model?
Yeah, okay, so the data missing in our additive manufacturing test was regular. We knew that. Because if you want to do the scanning of the sample for the entire time, you have to have...
Human brain. I mean, imagine you've got a brain and you've got a tumor and it's not right. But you train your model on, I guess, healthy patients? Or how do you detect that there is a tumor rather than there is a data missing in a brain?
So by data missing, I meant the projection data. Yeah, so if I scan the entire things with as many scanners as I have, I will be able to produce a good quality image. Now I have a missing part, which can be a missing angle, like in dental CT, or it can be missing like uniform missing data from that side. That's a good question. So as I said, we can set the pattern because the objective of the additive manufacturing CT was to reduce the amount of time that I go around the object from 12 hours to 1 hour. For medical application, it will be the same. So I know the sequence of a scan, but I don't know what is missing. So but I think I don't have an answer for that. I think if there is an area that is completely missed out of this scan, because the learning will do some interpolation between the missing parts. And if this is not observed in the data at all, because that's the nature of this straight line. It's just if it doesn't go through that and it doesn't have that information, you might actually miss that side. Yeah. Good question. I don't think there's.
I will show a video in mine if there was time, and I didn't want to catch it. There is a real reason, because when we make a baroscope video of a part which is moving, and if there's a damage, how do you detect the damage? That's why I asked the question.
Yeah. Very good question.
Excellent.
Pete.
I think Peter at the back. Yeah.
Hi, Manish. I had a quick question about the CFD. It was really interesting.
Yeah.
So you said it takes several months, and that's a perennial issue with some of these really complex, multidimensional simulations. Do you see a role for AI in improving the time of those type of complex analyses?
Yes. So I'm co-supervising a PhD student after you left. So it would have been your student, but that's actually an area of. In area of electric motor modeling. So taking the modeling of electric motor and let's identify just the very challenging part. So like nonlinearity of material, where it takes the program to go on and on and on and on and on. So I think there's an opportunity to identify a spot that you are interested in improving, and then focusing on that. And I think there's a gain there, potential gain there. But
yeah, really interesting. Thank you.
Thank you.
Excellent. Another question just here.
Thank you. I think this is a very critical problem. But how do you have any thought of can you quantify the trustworthiness of the predictions that's being provided by this AI approach with just limited scans? So
for which case?
For let's say the brand scan.
Yeah.
When you have limited number of scans.
Yeah.
And it's related to the first question. When you actually miss part of the data, and it gives you a prediction.
Yeah.
And how can you quantify how much you can trust on the prediction of how correct it is?
Yeah, I think it depends on the method that you're using. You get some statistical numbers from some of the methods, but actually this is the whole point of being engineer. So now we are seeing AI in a different way, because I think most of you are engineering here, and we are very skeptical about the outcome. So I think that report from NSF says exactly what you're saying, is that as an engineer we have different culture, and this culture will ask these kind of questions that then you don't trust the outcome just immediately after you're producing very very good number in terms of your performance. And to answer these two questions, I don't have a direct experience of actually doing.
Then you have confidence that very good model, and you should be aiming for a very high R square, perhaps about 0.95 or something. But in engineering, we sometimes work with even 0.6, 0.7.
Yeah.
So that's why the expert knowledge comes into it, if you don't have enough data. But there are standard tests for testing. I don't want to leave the presentation as gloomy that we don't trust AI.
No, I think we trust, but I think because this is by nature, we are very negative people. We don't believe this. You have to make things that always work. That's the challenge. As a mathematician, you don't have to do that. Yeah. Thank you.
Thank you very much. Fantastic. Round of applause, please. Okay, so our next speaker is Sharo Shapar. Fantastic. Thank you. a talk from two of our undergraduate students, Jake Howarth and Tansy Kelly, and they're going to talk to you a bit about the Dyson Institute.
All right. Hopefully your mic's working.
Hello.
Right.
It is.
Okay, so thank you for coming, everyone. Hopefully you're enjoying the conference so far. So we're going to talk to you, as James just introduced, a little bit about Dyson Institute itself and the student experience. If you can click on the next slide. So who are we? Well, I'm Jake. I'm a third-year undergraduate engineer. I take the electronics stream, which I'll describe shortly about how the streams work. And I'm in the energy storage research team. So I mainly do cell design in work, so kind of around the electrochemistry aspects, because Dyson, as is in the news, been in the news recently, is developing its own sort of battery technology. And this is Tansy.
Yeah. Hello. So I guess we just wanted to highlight the difference between the engineering education that we're currently receiving and one which we expect most people in the room have received, as you guys, most of you will have gone to university, and obviously we're getting our degree not through a university. So as Jake, I'm a year 3 undergrad, but I've decided to specialise in software engineering. And at the moment I'm working in systems engineering as well, which I'm really enjoying. So a little bit more on just what we're doing. Over to you, Jake.
Yeah, so I'm going to sort of roughly detail what the current diet program, note the current, is, as Beverly kind of introduced right at the start. So the degree, as Bev said, is an IET accredited BEng. Now, when students do this, we spend 3 days a week in the workplace, integrated into a work team, working on live projects. And for the students in my cohort, that doesn't contribute directly to the degree itself. That's linked to the apprenticeship. We do 2 years studying sort of a general engineering, and then we specialize into streams. And what we spend those other 2 days in the week doing is studying. So those streams can be, as I think Bev mentioned, electromechanical, electronics hardware, software, or pure mechanical. You spend those first 2 years doing sort of a generalized engineering to give you that sort of broader overview. And during those 2 first years, in the workplace, we do 4 6-month rotations around various different areas of the business. You will do at least 1 rotation in every sort of core discipline, i.e. electronics, software, and mechanical. You'll also do at least 1 research rotation and at least 1 sort of design rotation where you're doing the more sort of design aspects. And then you pick your chosen home team, it's referred to. So for me, that's energy storage research for your final 2 years, which allows you to sort of fully integrate into a single team and get that sort of cohesive workplace experience. And then at the same time as doing all of this, you're also working towards a level 6 product design and development degree apprenticeship alongside the BEng honours degree. So it's sort of like 2 for the price of 1, if you will. Also on a note with the workplace, they also try and integrate some international experience. Tansy and I are about to head off to Singapore for 2 months as a part of what's referred to as summer series. This allows us to go over and work in our what's referred to as a sister team. So Singapore is more of the sort of downstream stuff. So you get experience of the different type of engineering that goes on in Dyson in Southeast Asia, and also in working in different cultures and working with different teams. I think that's going to be quite a valuable experience, especially moving into the workplace later on, having that sort of more global understanding of the business and of just engineering in general. Next slide, please. I feel like I'm doing a COVID now.
I'll go first and then you can come up. So as Jake said, we spend the first 2 years rotating between 4 different teams, which is great because it means by the time we get to the start of our 3rd year, we know which engineering discipline we've enjoyed the most. So I spent 6 months in embedded software, which I really enjoyed, hence why I've now chosen software to specialize in. I was working on a hair care product. Again, not many women in the room, but it has since been released. So one of Dyson's latest products, the Air Straight, I helped write some of the safety code for that, which was really exciting. The team were really supportive in helping you learn because I was just joined the team. I was 18 years old and I was thrown into the project. It was agile, was given tickets, all in C. I had never coded before, but it was amazing. Everyone was just so great. I then spent some time in design engineering with hair care. It was a lot more relaxed, very chill, but I preferred the more structured, agile way of working with the software. I then went on to new product innovation in the wearables team. So that is sort of the headphones that have been released. It was the same team working on some stuff in there, which was really exciting. As it was brand new, it meant that you could make whatever decisions you wanted within your little part. So you had an awful lot of say in how it worked. And then also power electronics research for my electronics rotation, which was definitely the most technical rotation that I was in, but I really enjoyed it and I learned a lot. Over to you, Jake.
Yeah, so I've already said a little bit about my sort of workplace experience, so I won't take too long on this. But yeah, when I first started out, I started in electronics hardware. I think it's worth saying that also Diet do take into account, or at least they did for our year, what you'd be most comfortable in as your first team. So you're not, because you're sort of landing in the workplace immediately after having finished your A-levels. So you do potentially feel a little bit overwhelmed for the first few weeks, although workplace team is very supportive. So to try and ease that, I was sort of, a lot of my hobbies were around electronics, so electronics was my first sort of placement. That was really interesting. That was sort of core sort of electronics PCB design, really hardware-based in environmental care. I went into embedded software, wrote some code for actually, I think it's called the Wash G1. It's been released. It's like a wet floor cleaner. So I wrote some of the code for that, which was really interesting. Then I went into tech research, where I did a lot of rotodynamics, a lot of CFD, a lot of FEA as well, which was really good to have access to Dyson's resources as well. That was a lot of learning, especially considering I hadn't done any academic modules on rotodynamics, but it was great because that team has some of the smartest people I've met in Dyson and it was a brilliant experience. And then spent 6 months in NPI floor care, which is new product innovation, it's referred to, which is sort of creating sort of newer designs, and it's sort of the really early stage for blue sky kind of stuff. And then, as I said, at the moment, I'm mainly looking into electrochemistry, and there is some links with AI actually that I can't really talk about in much detail, but the team is sort of slowly, teams across the business, I think, are slowly sort of taking on board these kind of AI technologies, just trying to like mitigate any potential risks associated with taking them on, especially depending on the area. But yeah. Next slide, please.
Right, brilliant. So obviously we're working, we're studying, but there is also some fun. So right now we're all in our sort of student hub. So this is called the Roundhouse. I'm sure you can guess why. But yeah, obviously a bar opens in the evening sometimes, and then although you can't see it, behind all of here you've got the pods, so year one student accommodation. They're great. Each individual cuboid is a room, double bed, ensuite. We are spoiled, it's brilliant. The only downside is when it's pouring with rain in the morning, you have to put a raincoat on to go to the kitchen. But yeah, everybody loves it. Yeah, so I will. We also have our equivalent of a student union. It's been called the UEC. And Dyson, we love our acronyms. But because the institute is so new, we elect people in, and then our head rep sits on council within the Dyson Institute, which means they get a big say in how things are run, and it's all very exciting. And then our other reps also sit on other councils, such as academics, to make sure things are running smoothly, and we work with the staff a lot to make sure that it's the best experience it can be, which is really great. It's what we love about being such a small little place. There's 34 people in our year, so everyone knows everyone, 4-year groups. And as Beverly said, we have a new MSc starting in September, so we're really excited to be welcoming a lot more people along. So I guess our final bits, just
yeah, sure. So as Beverly said, the Institute is evolving. It's always evolving. So the provision of the apprenticeship is going to stop, and we're going to start offering the NEng course, offering that sort of higher level sort of academic provision, but the workplace element of that course isn't going to stop. It's going to be the same rotations as far as I'm aware. They're still going to get that amazing workplace experience, And I suppose one thing we haven't actually mentioned, but it is kind of relevant, especially when it comes to student experience, is the students here don't pay tuition fees and receive a salary for working. As a degree apprenticeship, that's obviously fairly standard, but it makes quite a big difference, obviously, as a student. It gives you quite a lot of freedom and sort of, I don't know, I think it's quite an important thing to consider when considering the student experience, I think, but yeah.
Yeah, I mean, it's obviously great that we don't pay for our degrees, but we're very busy, we enjoy our work, and both in the workplace and in lectures. And yeah, I think Jake's already touched on the fact we're excited to be spending the next 2 months in Singapore. We'll also be doing some trips over to Malaysia to see some of the manufacturing lines, just to give us, because we start the projects over in the UK and then they get handed over to Singapore. So by seeing both sides, we get to see the whole design process of the product, which we're really excited about. So thank you all for listening. If anyone has any questions, we are happy to answer them.
Okay, fantastic. Any questions for our students? Do we have a microphone available?
I've stolen the microphone.
Oh, I'll give you my microphone.
Hi. What would you have done if you didn't come here? Do you think you would have studied engineering somewhere else, or do you think you would have done an apprenticeship somewhere else?
I can start. Most of the people that come here have all applied to university through UCAS. I would have gone to Bristol to study engineering. On results day, it was just, I decided to come here instead, but I had my offer ready to go.
Yeah, and for me, I would have actually been doing physics at UCL, but then I decided to come here. And to be honest, I'm currently looking at, after graduating, trying to do a PhD, probably going to end up being either in physics or in chemistry, because it's going to be going down the route of staying in my team, doing sort of stuff around energy storage research, and stuff to do with various different spectroscopic techniques for advanced characterization.
Yeah, I think an important thing to note is that apprenticeships have changed a lot in the last few years. It's not people that haven't done very well in their A-levels and have got here. There's quite a few people that have turned down Oxbridge offers to come here. So things are definitely evolving and changing, and we're excited that we are a part of that, especially as we're the first year at Dyson to be awarded the Dyson degree rather than the Warwick degree. So when we graduate next year, hoping for a massive celebration, as we have been the guinea pigs in them trialing this new course on us. So there have been some little bumps along the road, but we did know what we were signing up for.
Yeah.
Maybe I can build on the previous question. I work with a lot of universities in UK, and one of the success factors for intake of students and graduates is the job that they can take. But you guys already got a job. So maybe it's too early to ask that question, but is there statistically people who will go through this program, do they stay with Dyson, or do they, I mean, usually want to do a PhD, but generally speaking, is it just like a stepping stone for you, or?
So we've had 3 years graduate so far with the Warwick program. I think about 5 people out of 90 have decided to move on somewhere else. Some of those people went to do a master's for a year and then have come back. When we graduate from here, we skip the grad program because we've already got 4 years of industry experience, and we get the option to spend 12 months in pretty much any Dyson site across the world. So we've got some people at the moment who are looking at possibly going to Brazil. People have been to Chicago, Amsterdam. Obviously, HQ is in Singapore, Malaysia, Philippines. So at 21, why wouldn't you want to stay and go explore the world with your company?
Fantastic. Any other questions?
Just a quick question. At which point you learn about IP in your studies?
IP is in intellectual property. Well, when we joined, I mean, IP is central to a lot of things when it comes to Dyson, because at the end of the day, the protection of our intellectual property is absolutely paramount. You get a lot of exposure to concepts regarding IP when you're in the workplace, because you're developing IP and having to protect it, and you're also exposed and privy to a lot of very confidential material about products that are many years down the line. So I guess you get that sort of real experience of that kind of thing, and we also have contacts with our own legal department and patent attorneys. So we get that experience by working with Dyson and the patent attorneys if necessary to protect IP. We do get in the beginning, because obviously you're straight out of A-levels, you don't necessarily have a particularly good appreciation for the whole IP side of things. So we do get some talks from legal departments and stuff, but there isn't sort of a formal module on IP per se.
Yeah. I mean, the patent attorneys are always there.
Yeah.
If you've done something wrong, you'll find out very quickly.
Know.
Okay, fantastic. I think that brings us to the end of our session here. So a few things. I mean, obviously, if you have more questions for our students, then please do find them during the lunch break. We've got some more students on the team wearing nice blue tops with Dyson Institute written on the front, if you have any questions for them. I think we've got a VR demo set up somewhere right at the back of the room. Where I am right now is the VR setup, which is concerning. Brilliant. We've got some lunch, which I think is going to be served, and Mehdi will be chairing our second session, which will start at 1 o'clock. But yeah, thank you so much for joining us for this first session, and have a really lovely lunch. Oh, sorry, actually, there are also some posters scattered around the room, so do engage with those. Do go and see what those look like, because yeah, they look pretty great. Thank you so much.
Hello again, everyone. We are starting the second session, so can you kindly come back to your chairs, please?
Even if I move this around in space, I kind of mess around with where it is, you'll find the sketch will stay attached. Okay, just pop it down on here.
Mehdi.
It's nice to meet you actually in person. Yeah.
So again, can I ask everyone to come back so we can start the afternoon session? Thank you. So our next speaker is Mike Mangan, and the title of the talk is Reverse Engineering Insects' Brains to Provide the Software Mind Enabling Machines to Move Like Natural Creatures. So let's have a round of applause for Mike.
Okay, thank you. So yeah, and thanks to the organisers for this event. I've really enjoyed it so far. There's been a lot of synergies that I've seen, even though people are coming from really different backgrounds. So thanks for putting it together, and thanks for inviting me. So yes, I'm Mike Mangan, and a slight change to the advertised programme. I was invited when I worked at the University of Sheffield, but I've just got a fellowship recently, which started a month or so ago. So actually, I'm now seconded from the university into a spin-out company called Opteran. And that's the logo that you have here, and that's the badge I'm wearing. And at Opteran, we look to enable machines to move like natural creatures. And the one thing I've learned from my time in industry so far is get to the answer quickly, stop waffling on. So with that, I'll show this 1-minute video, which will summarize everything that you need to know about my talk. Unfortunately, the sound isn't playing at the moment, so I'll just let you read what's on screen. So all the robots that you see here are robots that we've been producing in-house to solve these type of navigation problems. Okay, so if we jump on to the next slide, thank you. Yeah, so the reason DETRA for Opteran is that we reverse engineer insect brains. That is our start point, because I don't think the clicker won't work, right? No, yeah. So our start point is working from animal brains, because if you want to think about intelligence, I would argue intelligence is something that's really ephemeral and we find really difficult to define. But what we do is we see animals behaving autonomously in an intelligent way. Their behavior is intelligent. And that is our start point, is we want to produce robots that can behave with similar levels of autonomy and intelligence. And what we want to do is produce the software mind that enables these robots to move like natural creatures. And the key thing as well, the second point I want you to get is, our business model is to be a software company. What you're going to see throughout is we're going to show off some hardware. But what we've been doing is building hardware to show people how the technology can work. But actually, we're a B2B business. We sell to robot suppliers, systems integrators, who are then selling to their customer. So you could think about our business model as something akin to ARM, where we sell reference designs for both the hardware and the software, So if you were looking for low power compute, you would get an ARM design, but you would have a supplier that would build that into a chip, which then ends up in your Apple product. We want to be that type of system for autonomy. Yep. So you should be asking yourself, do we really need new robots? We keep getting told that self-driving cars are another 2 years away, and another 2 years, and another 2 years. And basically this slide tries to capture, we've now been running for 4 years, so this is the market feedback that we've been getting, is that we're still struggling to build adaptable machines. And being good scientists, we wanted to make a lovely graph about this that we could quantify exactly where we are, but I'll speak you through it. And what we've got is we've got these 6 dimensions. So if you think about where robots are being deployed today, the vast majority of robots that you see are either in your back garden or they're in warehouses. Both of those environments are very highly augmented. I actually put a robot in my back garden last weekend and I had to put the perimeter wire in there. It was actually quite depressing when the kids were asking me how this robot gets around and it's just random and hitting a wire. If you're within warehousing, you can see that they're getting humans out of the loop. If you go to the Ocado's factories, you've got robots on rails. You've got no humans in there. It's completely in the dark. So it's not that we've taken our robots out of the lab into the real world. It's that we've turned the real world into a lab, is where we're at the moment. The next thing that we have is environmental conditions, is that the systems that we have right now are really intolerant to change. So I was in a building very similar to this one at the European Robotics Forum last year. And I spoke to one of the biggest suppliers of pallet carrying robots. And there was a lovely demo. The thing was moving around here and it was avoiding people, etc. And I asked the member of staff, would it be able to go outside into the courtyard and get a pallet off the back of the lorry? They said, not a chance. If this thing goes outside, the light levels are too contrasting and the sensors are essentially blind. So that gives you an idea about the limitations in terms of tolerance. And then you've got environmental dynamics. This is where your environment is changing from time to time. So you can imagine a robot navigating a space like this at the moment where you have lots of people. Essentially, people start contaminating things like the maps of the environment. If we move these chairs around, it doesn't matter to us that you've come in here. I guess these chairs aren't here all the time, right? But you still knew how to move around and not crash into things. You didn't think this was a different roundhouse building. You know, we have tolerance to that, but the systems that we have don't. And again, just to quantify this, I spoke to one of the biggest suppliers of warehouse robots, a different company this time, and asked them what their process is. So they send an engineer out to a warehouse. They'll then drive the robot around and map the environment. And then it usually takes about 2 weeks, more or less, of compute offline before you can give them the map back. If you want to change that map, you need to do another 2 weeks. So actually, if you want manufacturing 4.0 and you want flexible supply chains, reactive and agile supply chains, the current systems are not working there. We're solving the problem of yesteryear rather than next year. So I'm not going to talk about the 2 in the bottom left for the purposes of time, but you can imagine that all 5 of these first things are really, you could crunch it down and just say there's too many edge cases at the moment for industry to take on board robots. The performance just isn't up to scratch. And in the last area, which when I came into this as a scientist, I didn't really think this would be an issue, especially in things like autonomous vehicles. But size, weight, power are all a massive issue at the moment. So if you look at self-driving cars, they've generally got the laser scanner on top. You've got multiple radars. We got a bill of materials recently for a self-driving car. It's north of $30,000 of sensing equipment that was on board recent self-driving cars before you've put an engine inside it. So you can imagine that this is not going to sell very well. And you'll note that Tesla have recently got rid of all their radars. That seems to be a cost thing rather than a technical thing. Okay. So that's where we are at the moment. Next slide, please. And if we were to look, so that was the commercial setting of where we are. And now if we look at the technical approaches, there's basically two approaches we would say right now to trying to solve this adaptability problem. The last 10 to 15 years have really been everything on the left-hand side. So you could see that we started with expert systems like SLAM. These have recently been augmented or been replaced with artificial intelligence. So what you had here was you had essentially humans creating algorithms. If you're using a deep learning system, you're using this caricature of a biological system, which has the neural network architecture, and it has learning rules, and they were brought in to try and deal with a lot of noise in the environment that the hand-coded systems couldn't deal with. And actually, we would argue, I know we heard earlier that there's a lot of data in the world. I would argue that these systems are getting trained with hardly any data, Now that's going to sound nuts, because if you know that the recent ChatGPT was trained on the entire internet, but let me come back in a minute to the comparison. Where we would say with these things are, it's a bit of a leap of faith that they're going to work, because we've not got any examples that they can solve this autonomy problem. Okay? We're sort of generalizing from the fact that you can play chess, you can play Go, you can do language models. We're generalizing and making a leap of faith that it's going to transfer back into robotics. What we're trying to do at Opteran is follow a different approach, which we call natural intelligence. And that's to extract nature's algorithms. And if you think that evolution over billions of years has essentially been trying to solve the problem that we want in robotics, which is autonomy. It's moving about in the real world. And that's where evolution started. It didn't start from language. It didn't start from playing puzzles. It learned how to move around in the environment first, and then all those other things came later. And if you think about data comparisons, every brain that's ever existed was there to move a body around in the real environment. So every second that they're collecting data, that's the level of training data that we're trying to compete with in the more engineered approaches. But the thing that really, the kicker that always gets me, is we know it works. You can look outside of the window if it's not raining too much, and you'll see bees and such like birds flying around, solving many of the problems that we want in autonomy right now. You know, there's evidence of proof right there that this is solvable. We just need to understand how. Yep. And this is the approach that we've been following at Opteran. So this summarizes the approach that we take to addressing this issue. So if we look into the middle first, this is essentially our recipe for developing autonomous robots that are inspired by real brains. The first thing that we do is we identify valuable natural behaviors that we see in nature. So to give you an example, if you look to the left, this is all our inspirations in the brains. The butterfly that's in the middle, this is the monarch butterfly, and they actually overwinter in Mexico, and then they'll fly to their summer breeding grounds in Canada, and they'll actually only make the journey in one direction. But the next generation will find their way back to the same trees in Mexico. So in terms of how well they can navigate, you know, these guys are an excellent example. So that would be an example where we'd want something similar in robotics. What we then do is we've got a real strong background in computational neuroscience. So we separate algorithms from neural implementation, and this bit's really important. What we don't do as a company is take a facsimile copy of a neural network that we see in biology and deploy it onto a system. What we do is we understand how the system's working. We then have a mathematical derivation, which first we can patent, but then we can take this to the next step, is we can map this onto standard compute hardware. And this has been really important for us to get commercial momentum. We're not reliant on a spiky neural network chip. We're not reliant on a specific FPGA implementation. We can go to a customer and say, well, why don't you try out our algorithms? Oh, and you've got a spare bit of CPU space. Good, we can deploy that as a software code. The other thing that's of value here is because we've got the mathematical derivation, in comparison to a lot of these learned models, we're much more white box. So you could think that we've essentially went back in time, that we're deploying an expert system, but it's bio-derived, okay? And then what this allows us to do is once we get to this source of algorithms, we actually deploy this into what we call Opteran Mind. So if we jump to the next slide. And this is our actual product at the moment. So we have our Opteran Mind. 4.1's already been released to certain clients. And it's made up of 4 levels. So what we see at the bottom in these bright colors is you've got our Opteran Vision system. And don't worry, I'm going to show you some nice pictures and videos soon to make this less dry. But the key thing here is we've got 360 degrees vision, and it's algorithmically stabilized. And this is really important because it turns out that sensing the world in the right way is really important. And from a lot of the engineering perspective, we've maybe been doing it in the wrong way. If you think about in your mobile phone cameras, you know, we've got more and more pixels, which gives you more and more data to crunch through, and you've got a very narrow field of view. This leads you to a lot of overfitting, it turns out. And I'll show you some examples of that. So getting the sensing right is really important. We've then got our perception layer. So these are bio-inspired visual processing algorithms, which brings us tolerance to things like the lighting changes. So when I spoke to you about going inside to outside, we've got examples of that, and I'll show you a nice example of the video. But also it gives us tolerance to things like dirt and adverse weather conditions. Opteran action, you could think of as almost the reflexive layer. So this is your very fast action. So this is our collision avoidance. Interestingly, this was actually the first patent that the company was founded upon. We found the circuits that were doing super efficient optical flow calculations in the insect brain, orders of magnitude less than what you see in engineered systems. And that can be used to do stereo and dynamic depth perception. And the key thing is these bright colors at the bottom, vision, perception, and action. These are the fundamental building blocks that it turns out if you get them right, that then you can build these higher level capabilities. So you can see what we've got in the top level in the blue is our cognitive engines. So right now we're deploying our spatial engine. So this is GPS-free, visual inertial odometry, and localization. And not only is it super robust, it's super lightweight. So we've been doing some maths on this and doing some tests, and we think we're about 1 kilobyte per square meter in order to map an environment, which once you start mapping at scale, this becomes really, really important. Not just in terms of memory use, but in terms of your compute use to search through that space to find where you are. Okay, so if we jump to the next slide, please. So just to let you into some of the secrets that I've been talking about, what have we learned from studying nature that is maybe slightly different to what we would have come up with if we were to try and design this from the ground up, is that capturing the right information is absolutely fundamental, and sometimes it's not clear what the right information is. So this is what we call an Optran development kit. So this is how we speak to clients. When I said we do build some hardware in-house, this is how we speak to clients. We actually build this and let them test it in their environment. And what you have here is you've got a super cheap sensor. So what you've got is this guy here is essentially 2 very standard CMOS sensors. And what they're doing is each of them are pointing. One's up pointing up, one's pointing down, and then they point through a fisheye lens. So what you'll see in some of my videos in a minute is they've essentially got fully spherical vision. And this is what we see not just in insects where you'll recognize bug eyes, but actually your vision is really wide field of view. I mean, I can pretty much see my hand right now. But it turns out perception plays a trick on me. I feel like my hand's colored. I can see color. That's not true. I know that my fovea is jumping around like this. But weirdly, a lot of the cameras that we develop seem to be trying to replicate what we perceive rather than what we actually sense. We are trying to mimic what you actually sense to get the right information. So all the videos I'm going to show you that are coming, the features of this is it's got really robust light range, so we can go from 20 to 3000 lux. It's running at 90 FPS, and everything that's running on board is running fully there. And everything that's processed on board is running with 0 latency. So we've actually got a little piece of electronics in the middle for our demos, which is running all the code as well. So we're not uploading this into a data center. We're connected to Wi-Fi because we record the ROS bags, and we can talk to the system and see where it is. But everything is going to be happening on board. Next slide, please. The next thing is it's not just about what information you process, it's about what order you process that information. So if you look at a natural system, this bee, we start on this side, this bee that's inspecting a flower, it stabilizes its head mechanically. And you might have seen, I don't know if people have seen those weird videos on YouTube where people hold a chicken and they move it around, and they're moving it around like this, the chicken's head will stay in exactly the same place. So it's actively sort of keeping itself like this. If you haven't, do it tonight, it's great. So what we've got is we've got a patented algorithm that is doing stabilization electronically on our system. Okay, so what you're seeing here is Cara, who's actually from PhD at Bristol, which is really a nice link. And Cara, what she's doing is she's waving around one of her ODKs. So you can see that there's movement translationally, but it's being stabilized rotationally. She's actually waving it around like this. And what's happening is this is being stabilized. And what that does, stabilizing that information physically, means that the compute that we have to do afterwards is so much less. Okay? And if we jump to the next slide, please. So what you're going to see is now we're stabilizing the information through processing. So in the top one here, this is the real world view from our camera in our lab, and you can see the lights have just been switched off, and look how dark it got. And the lights will come back on again. We were having a lot of clients that were trying out different SLAM algorithms, and they were telling us they had a real issue with changing light conditions. So if you were to be, your robot was learning this environment now, you've got these big glass walls, lots of light over here. Then you come back in tonight, and the light's coming from above. This is all, you've actually inverted your field of view because now this is dark instead of being bright. Your robot doesn't recognize where it is. And just to quantify the type of issues, so there's a lot of companies that are trying to develop autonomous systems, trying out lots of tech. One company were speaking to us, they were trying to do drones. They were running a competitor algorithm, and they said when it was in the same space, but it was now mimicking nighttime. And what was happening was, it wasn't that the system was aware that it just didn't recognize places. It would get confused about where it was on its map, and it would suddenly shoot in the wrong direction. So what they were happening was they had like a simulated house, and then what would happen is this drone would just shoot over everyone's head, and it was very unpredictable and deterministic. So this is one of the, when I was speaking to you about robustness in edge cases, this is one of the issues that people are having. So if you're a supplier of drones, you just cannot deploy that type of system at the moment because it's just not worth the risk. Even if it's one in 1,000 times, it's just not, it's simply not feasible. But if we're going to play that again, what you'll now see in the bottom, sorry, I went off on a tangent, is this is the same scene, and what's now happening is this is our insect-derived illumination and variance algorithms. So it's taking that input and it's stabilizing it. And what you'll see is the lights are going on and off, but the screens and stuff, the key information has been kept. And then this one, you've got a big bright uplighter in the corner, which you can imagine being in the house. It's going to switch from on to off. You can see how much the top one changed, and our one stabilized here. So it seems like the animal is not just getting the right information at source, but then it's processing it such that it's very stable regardless of the conditions that you see yourself in. Okay, so we jump to the next slide, please. So don't play this one yet, I'll just... So the real story of this is we've seen another competitor that launched their navigation system, but they warned that there was issues if you had mirrors in your environment, which would essentially be like everyone's bathrooms and bedrooms. So we went off to IKEA and bought a whole bunch of mirrors, and our system seemed to be okay. So we then commissioned getting a lovely video put up. So what you're going to see here is this is the hardest test we could think about for our navigation stack. So what you're going to see is one of those iCreate robots, which is essentially like a Roomba vacuum cleaner. It's going to have one of our ODKs on top, and it was going to be driven by Chen through this environment, which is a maze of mirrors. And it's going to have nice lighting when it's learning, and then when it's following the route back again, the lighting is going to be changing in the most difficult way we could come up with, and you'll see how it works. So if we play it now. Oh. So when it zooms out in a moment, yeah, you can see that we made this maze full of mirrors for the system. And it turns out if you've got a laser scanner here, you've just got too many reflections and you don't get the right type of input. And supposedly for some visual SLAM algorithms, this is also causing serious problems. And now it's meant to be navigating, and you can see the lights are switching on and off in a random pattern. And the system isn't affected at all. And I should say it's not that we've programmed in a specific mirror use case, that now we're in the mirror environment, we need to do something different. This type of robustness just pops out for free once you're sensing the world and processing the information in the right order. And it'll make its way back to the beginning. There's nothing more interesting happens, so we can jump on. Okay, so where we're at the moment is that we feel like we've made significant progress against this sort of simultaneous location and mapping problem in navigation. And if you remember right back to that first slide where I tried to categorize the 2 dimensions on which robots are struggling to penetrate the autonomy industry at the moment, is you've got real world robustness. So if you take one of the, perfect, if you take one of the slides, or one of the examples, if you look at blinding and reflections, we're actually getting much stronger performance already than 2D and 3D LiDAR. And also we're competitive, if not better, than visual SLAM algorithms. And in terms in the bottom of radically lower costs, because this is standard compute, standard old sensors that can be augmented, the bill of materials is through the floor. So if we jump to the next one. And the biggest thing that we can say about how this is working is we just announced a big strategic partnership in the last month or so with one of the big suppliers within to the autonomous the warehousing robot industry with AMRs, a company called SafeLog, and they're very conservative, small c, in terms of the technologies that they take on board. So we've now got a strategic partnership to be rolling out with them. Yep. In terms of the company, we're up to about 50 people. So we're based here in the UK. Our engineering team's in Sheffield, where we've got about a count of 30, quite a lot of PhDs. And we've got our commercial office in London. We've also got a footprint in the US, and we've received a whole bunch of other awards. Yeah. So if you were to remember one thing from this talk today, I'd like you just to remember that we would argue that our intelligence isn't artificial, it's actually natural. And with that, thank you for your time.
Thank you very much. I guess next time I'm watching one of James Bond movies, I'm going to understand what's happening with those instincts.
Yeah.
Flying into the enemy bases. Any questions? Yes.
You were behind. Shall I go first? Go ahead, yeah. It's a quick one. Solving the reflection problem is very interesting for my application I showed earlier as well. But one of the problem I have in what I'm interested in is getting a sense of depth, how far you are from the object.
Yeah.
Is that something you are working on so you can actually get that?
So the ODK3 that had the two...
You can actually measure it accurately.
Exactly. So suddenly you've got stereo vision, and we know that even within insects, a praying mantis is using stereo. So yeah, stereo vision is on our pathway, but there's other ways to get depth perception from a single camera as well. So yeah, this is part of our the next release, the collision avoidance release.
Oh, thanks a lot. Yeah, how do you do mapping? How do you represent space?
Oh, that's the old how question. I don't know how much I'm allowed to. So we've got a patent in at the moment about our localization. So what can I say? I mean, we're still using vision, right? So we're still using the same fundamental information. So we're still encoding locations using space. But the way that we do that, the information that we capture seems to be unique in comparison to standard computer vision algorithms. Unfortunately, can't go too much more into that because the patent's still going through.
Okay, I mean, you're making some big claims, and they're a little hard to believe, to be honest.
Any particular ones that I can answer on, like rather than the how and the what would be the.
Let's talk later.
Okay, sure. Yeah.
But just better than SLAM, is what you're saying.
Yeah. So I asked about that before I came. Like, what could I claim? So yeah, we can talk about our localization. Could I jump back 2 slides? Could I jump back a couple of slides? Sorry, there's the one that's got the different graphs. Yeah. So this one. Yeah, so in here, in terms of our positioning accuracy, within an environment like this one, what we've measured and what clients have been measuring is down at 2 centimeter level within something like an indoor space like this. In a much more open environment, we're usually within 5 centimeters, because that's the tolerances that are given to us by clients that in order to fulfill the safe log contract and whatnot. So we've not been doing benchmarking academically where we compare with everyone else. But rather, the clients will come to us and they'll say, can you work here? Like, lighting conditions would be another one. In order to open up a contract, we had a customer tell us lighting is the thing that blocks them the most. And then what we do is we demonstrate that can work and then move to contract. So those type of things were crucial for nailing the safe log contract.
I mean, I very much agree with a lot of your arguments, and the performance you're claiming sounds great. I'd love to know more about how it works. So
yeah.
Thanks a lot.
Thanks, Andy.
I guess we have one more question there.
Very interesting talk, thank you. I have a question around the scalability in terms of the number of agents. Have you considered that? Because, I imagine these systems, for example, some of the work we're doing is on drones. So how would this system be useful for tiny robots, and how does it scale to 10, 20 drones? How do they learn? How do they interact? Is it something that you are considering for follows up of your company? Or
one of the founders of the company is actually an expert in decentralized decision making and swarm behavior. So James Marshall, that was in charge of the company, that's his background. It's something that we have in our research and product roadmap as a future piece of work, but what we've realized is when we went out speaking to customers, it was quite an interesting example that customers were interested in is demonstrating spatial and localization more than they were collision avoidance, because actually in a lot of these environments they're very well controlled. And the swarm robots is a similar one. It's far down the line in terms of what customers are actually asking us for. They're not coming to us saying that they want us to demonstrate localization in a single robot, and then we'll go from there. And usually when you said scalability, I thought you were going to say size of space. So that's another one that gets asked about. So that's why we've measured, for example, the memory footprint that we have. But yeah, I mean, insects are the classic example, right? Insects.
Yeah, no, exactly. Because I did my PhD at the University of Sheffield, and
cool.
I know James Marshall
Cool.
personally. So yeah, I was wondering, since now I'm working on swarm robotics, if there's like an immediate next step that you see, and in terms also of applications.
Yeah, for sure. And what you see in insects is there's not a centralized controller. So what we've heard from a lot of customers is one of the problems with deploying robots in Europe especially is when you've got to add infrastructure. And things like Wi-Fi does become an issue for them. So when you've got things like robots clustering around chargers, which is quite a common problem. And how do they make the decision to say, okay, the charger's busy, I'll keep doing tasks, I'm okay for now. So I can see applications, but they're not being asked for at the moment. So the commercial drive for them is not there this second.
Thank you. So let's thank you again for your great talk. Next, we have Professor Sabine Hart from University of Bristol, and she's going to talk on swarms for everyday environment.
Great, thank you very much for the invitation, and that question was a great segue into my talk. I'll be telling you about my journey engineering swarms across scales from nanoparticles for cancer treatments to robots that I hope will be used in everyday environments. And for, I'd say, the last 15, 20 years, we've been really focusing on the science of engineering. What is that? Well, if you look at this flock of birds, they can do beautiful, complex dances in the sky. And there's many features that are useful for engineering. For example, if you keep adding birds to the flock, it continues to flock, so it can scale to huge numbers. If a bird crashes to the ground, the whole flock doesn't crash, so they're robust to individual failure. And together, they can do more than the sum of their parts. For example, they're better at avoiding predators as collectives. How does this arise? It's not the result of a leader bird telling every bird what to do. Instead, it's the result of every bird reacting to the local world around them, and each bird follows a simple set of rules, and that gives rise to these beautiful flocking patterns. Now, there's examples of self-organization everywhere around us in nature, whether it's flocks of birds or ants as they create a trail to your picnic table, bees as they make decisions about their next nest site, or our ability to grow fully functioning human beings from just a couple cells. And what's fascinating for us as swarm engineers is how does that work? Well, for us, the way we do that is we need to crack a puzzle. Given a collective behavior we want to achieve, such as flocking, trail formation, decision making, being able to grow functional shapes, we need to find the agent and its local interactions that give rise to that desired collective behavior. So how do we do that? Well, we use two different techniques. One is to use bioinspiration. So we talk to the biologists who study the bees and the ants and the birds and the cells, and they give us rules that we can put on artificial robotic systems. And when we do that, you can see here some of the robot swarms in our lab. This is, and also at EPFL in Lausanne. So in the upper left corner is a video that's not running right now of a swarm of flocking robots that do flocking patterns. You have robots here which are coin-sized. There are 100 of them in the lab here in Bristol, and they're doing trails, inspired from how the ants create trails. Bottom left, that's 400 robots making decisions between blue and red. So you see them all turn blue because they make the right decision. And at the bottom right, you will have seen a swarm of 300 robots that grow shapes, basically like little fingers or little limbs, by having these robotic cells communicate to each other and share very simple information. So that's one strategy, the bioinspiration. But we also do a lot of automatic exploration or machine learning, or to be more precise, artificial evolution. And you heard great examples of genetic algorithms this morning. We do this when we don't know what rules of swarming will work. So typically we'll give a problem to our swarm. For example, here the swarm needs to move the frisbee to the right side of the environment. And in this case, the robots have a GPU on board, and they're each running artificial evolution. And in 15 minutes, in real time, without any external computation, they can learn to push this frisbee from the center of the environment to the right side of the environment. In addition, we do care about knowing what our robots are doing. And so the things that we evolve are behavior trees taken from the gaming industry to describe the behavior of characters. And these behavior trees are readable by us. We can color code them when we run simulations. And so it helps us understand what's happening within our swarm system. We also can automatically extract behaviors from videos. So we could look at a behavior here of our robots at the bottom left, or in the future, we hope of natural systems. We're working with biologists to do this. And by looking at videos of swarms, we hope to extract behaviors, so those behavior trees, so that we can explain the swarm behaviors, translate them to robotic systems, and perhaps control them, for example, if that swarm was a nefarious swarm. So here's an example of an extraction where on the left we show a video in simulation of a swarm behavior. You see robots moving around, picking up boxes. And then on the right you see an example through an evolutionary process again of an extracted behavior. And luckily these two behaviors are the same. So after these 20 years or so of doing the science of swarm engineering, we're now at a stage where we know how to design algorithms, both using bioinspiration and automatically using machine learning. And increasingly, we have hardware that's either very simple but works in huge numbers, or more and more sophisticated, like those robots with GPUs. And so it's about time that we start thinking about making swarms for people. And so in this journey, the first thing that we did was to ask people what they thought swarms should do. To do that, we set up a little escape room before COVID when we were allowed to lock people into small spaces. And we taught them about swarm engineering by cracking a bunch of swarm puzzles. And then we asked them where they thought swarms could be useful. And a lot of them, they're areas that we've been thinking about in our research world. You could do construction, you could do search and rescue, you could do farming, you could clean the ocean of plastic. You could do surgery if you're thinking of micro or nano robots in the body, massages, which is maybe not one that I had thought of, but maybe that's a product for Dyson in the future, a swarm massage system. And so we've been trying to take on board some of these ideas and deploy swarms across scales. I'll only spend a tiny bit of time on the tiny scale, but if you're interested in that, come talk to me during the break. At the nanoscale, we look at how trillions, actually 10 to the power 13 nanoparticles, are very good vehicles to deliver drugs to certain types of tumors. And because of that huge number, those vehicles, if you think about how to design them in terms of their size, their shape, their coding, you can't program them like a robot, but you can design the right particle. Then you can optimize how 10 to the power 13 distribute over tumor tissues. And in fact, we do that by growing virtual tumors, cutting them up into small slices, and again running artificial evolution to change the design of the particle so all those particles as a collective go in a tumor and are able to optimally treat those cancer cells. At the microscale, we think of microswarms. So if you think of cells, if you think of bacteria, those are all systems that work at the microscale in the millions, even beyond. And so can you control those types of swarms for biomedical applications? And for that, we create new devices. This is a desktop device, all open hardware, that allows us to control cells in a wound. So here you're looking at a wound in this device. And what we can do with this robot device is zap cells on the edge of the wound, and that helps drive the wound healing process. So we're controlling a swarm of cells in this case. And at the macro scale, we're getting back to the real robots, or the bigger robots that you're used to, so hopefully this is a bit more comfortable. We're looking at how we can make social swarms that interact in human environments. Here what you're seeing is a swarm of tiles. They're screens on wheels. We have 100 of them that we've built in the lab, and we use them to interact with people. We've used them as puzzles, so kids can work with the swarm to assemble puzzles in this case. We've used them as online pixels, so people can connect to the robots, control the pixel robots, and then you see what art emerges. So for example, they create a little football player, which I guess is appropriate for the Euro. And we've used them to ask people about their opinion on important topics. For example, at a mall in Bristol, we've asked people about climate change and what they would do to fight climate change. And people would select take more public transport, eat more vegetables, and their opinion then lived on the robot as a physical avatar of their opinion. So maybe people who are a bit shy, who don't want to interact with other technologies, a lot of them stopped by, interacted with their robots, and their opinion lived on to mingle with the others who were there. We've also used them as smart post-it notes where people could enter their opinion about climate change, and once the opinion is entered, you can put that on the floor, and they cluster a little bit like post-it notes when you reorganize them on a brainstorming board, but they do this automatically, and the clusters change over the duration of the day, depending on what inputs are put into the system. So here it's looking for its cluster. We're also looking at how to deploy swarms of very large aircrafts to detect forest fires and mitigate them early on. We were in Cornwall just last week controlling a swarm of these aircrafts, which can travel 1,000 kilometers and carry 100 kilos, so they can travel long distances. And in our simulations, we have many algorithms to be able to take huge areas the size of California, chop them up into different segments, or do other algorithms that are a little bit more bio-inspired or inspired from how the birds or ants operate, and then control those swarms over huge scales, over long durations. As part of our trials, an important thing has been to talk to firefighters. So we've spoken to 50 firefighters around the world to ask them how they can move away from being drone remote controllers, which they currently are, to being swarm operators. These are the trials from last year. We can't yet show the ones from this year. So these are the smaller aircrafts that we use to trial some of this. But a lot of it has to do with what's the interface to the swarm, so that the firefighters feel like they understand what the swarm is doing, and that they can quickly click a button that says search or drop a payload on that fire before the fire grows out of control. And we've been working with biologists to help, I guess, give back to the biologists and help them understand what's happening in the natural world. This is a project looking at how we can use a swarm of surface-based robots that have underwater imaging capabilities to be able to look at basking sharks. And it turns out that these basking sharks have amazing raker gills that can collect plankton, which is about the same size as microplastics. So our colleagues in the material science side are interested in understanding how they do that. And so they needed some close-up stills. I did mention everyday environments, and we are getting there. One thing that I've been fascinated about is the potential to use robot swarms in logistics as out-of-the-box solutions. And I think if you think of large numbers of robots, you might think of big companies like Amazon or Ocado that have very nice solutions for their warehouses. And many of these systems, the infrastructure, as we heard in the presentation before, is built for the robot. So you need to invest in infrastructure. You need to invest in R&D to build the right robot for the project that you're interested in deploying within your warehouses. I think swarms, because they operate in this distributed way, have the opportunity to be used out of the box. And so this opens up new avenues in small retail, people who wouldn't adopt robots who don't want to invest R&D up front, but want to be able to take a robot out of the box and use it in their environment. Pop-up warehouses, reconfigurable manufacturing, basically places that are a little bit more messy. And let me tell you why I think swarms make sense in that setting. So I use this as an example often. It's a cloakroom scenario. Imagine you arrived today at this symposium, and there was a cloakroom over there in the corner. You could have set it up in a centralized way. So let's say you're the operator of the cloakroom. You arrive, you map the environment beforehand, you put a central computer, and then people arrive with their jacket to the central computer and say, computer, please, here's my jacket. That computer says, robot 1, 2, 3, follow this trajectory, pick up the jacket, robot 1, 2, 3, follow this trajectory, and store it in this location. At the end of the day, you do the same thing again. You go pick up your jacket, and that central computer coordinates the pickup of your jacket. Now that works, but it required you to create a map of the environment. It required communication to work. It required that central computer to work efficiently. And it required the database of where your jacket was stored to always be correct and up to date. If you do this in a more out-of-the-box swarmy way, the way the operator would set that up is they would delimit an area of this environment, maybe with tape on the floor, and then you would arrive with an app on your phone, and you would say, hey, I have a jacket. And the nearby robot would come, pick up your jacket, and perhaps deposit it anywhere. It might look very messy, anywhere in that cloakroom environment. And then when you arrive at the end of the day, you take your Bluetooth app out, stop somewhere on the edge of that environment and say, has someone seen my jacket? And just like humans operate cloakrooms, the robots, because there's enough of them, would look around, pick up your jacket, and bring it to you. So in that setting, there was no central communication needing, there was no map needing, there was no database needed because it's always real-time lookup of the information that's present in the environment. And what it required was for these robots to understand enough about the local world around them to interact with them, to interact with that environment. And so we were excited about this potential, and we didn't have a robot to help us do that at the time in the swarm world. And so we've been building this new platform for the past 4 years, which is a new swarm platform that has more capabilities. So it has 4 cameras, it has a laser time of range sensor, it has four CPUs, it has a GPU, it has a lifter to be able to carry material. It runs very fast. It has a long battery life of 6-7 hours. And it's been built along with an arena that allows us to trial some of these ideas. So here what you're looking is a swarm of these dots for distributed organization and transport system. They're only using onboard sensing and computation. They look quite messy, right? They were doing random walks. They were looking around for those carriers, picking them up, and bringing them to one side of the environment. This is a baseline algorithm, just a random walk. But again, if you have enough robots, they'll see the carrier, they'll move around, they'll deposit it quite efficiently. And increasingly, we're able to make these robots a little bit smarter in terms of how they understand the world around them and how they share information. So we've been adopting the work by Andy Davison and Gaussian belief propagation to help our robots have better distributed spatial awareness. So hopefully you'll learn a little bit more about that in his talk later today. But fundamentally, what our dots do is that they have an idea of where the center of the world is. And at the start, every robot thinks it's the center of the world. And by exchanging information through local exchanges, over time, they converge to what they think is the center of the world. And because they all think the center of the world is the same, they're able to do behaviors that are more clever in terms of how the robots move. So here you're looking at a simulation where robots exchange information. That's all the links that you see. And here we're applying 2 swarm algorithms. This one is a shape formation algorithm. So because they understand something about the world, they're able to do more interesting swarm behaviors, but still in a very distributed way. So each robot here is trying to converge to a different shape. And on the left, this is a logistics application where they're trying to map where the boxes are. And you can see these boxes move over time, so it takes a bit of time for the update to happen in terms of the information. But what's beautiful is you can also drive the behavior of the robots to seek information. And so on the left, at some point, you should see them look very flocky. And that's just because they've adopted a new algorithm where they go to look for information to improve their understanding of the world around them. This distributed spatial awareness has opened up through a collaboration as part of our European project Emerge on emergent awareness from minimal collectives, thinking around what awareness is useful for robots. So what you saw before was spatial awareness, but you can also have temporal awareness, bodily awareness, situational awareness, object awareness, metacognitive awareness, the fact that you're aware, basically being aware that you're aware. And so we're really interested in how do you select the right awareness for your robots, and how do you optimize your behavior, perhaps using evolution, given that awareness or your capacity that you're given. And the hope is that by having robots that are more and more aware of their behavior, but also whether the collective is aware of what the collective is trying to do, whether that makes it easy for us to design them in a more narrow sense, so robots can do one thing, but they can communicate it really well to the outside world. So that allows us to optimize for ethical constraints, for environmental constraints, but then you can really scale up the capabilities of your system because they're better able to work together. With this idea of sharing awareness, one thing that we've been exploring as well is whether we can have a level above the swarm, let's call it a hive mind, and whether this collective, it's basically a cloud, okay? And this cloud stores information about what's happening in the world. So here's a task where robots need to deposit colored boxes on the numbers with certain colors, okay? So a yellow box on the number 1, which is yellow here. And you could do this in a very swarmy way, just like the random walk you saw before, where the robots are buzzing around randomly trying to put a yellow box on a yellow square, and it works or it doesn't work depending on what it's carrying. And that will work in a very baseline way. But you can also have them coordinate by storing in the cloud what box they found, and where they've deposited. So the cloud is not controlling the swarm. The swarm remains distributed in its intelligence, but it's putting some information in the cloud. And that cloud is readable based on requests from the robots. And so based on this type of sharing, we're learning how best to operate our system so the intelligence stays on the robots, but some information sharing happens to enable this coordination. And we do get pretty good performance gains. So swarms for everyday environments, what are those everyday environments? Well, they're communities. And so as part of the CSRC Center for Socio-Digital Futures, we're also asking, what do people want swarms in local communities to look like? In my mind, these swarms should be everywhere, right? You should have little robots in every corner street, in your office, in your building, and in your homes. And these robots, from a logistics sense, could just help you move things around. So you could imagine that you want to swap genes with your neighbor, and you call the local neighborhood robot. It takes the genes and it brings it to your neighbor. Or you want to pick up a coffee from your local coffee shop. Or perhaps you want to be able to just take all those packages that get delivered to the wrong place in your neighborhood and bring them to the right address. So in my mind, this makes sense. But is that what people think? Would they rather ring at someone's doorbell to give them, the pair of jeans? And so there's a big question around what should society look like and how do you best deploy these? And one thing that comes up over and over again is, okay, swarms for community, but how do you make them trustworthy? This is, say, the first 3 years of really thinking about this. And I'd say we've only scratched the surface. But one thing we've started to look at is how do we make swarms safer? And that's both the robots, how do you make the robots safer, but also how do you make the swarm behavior safer and these emergent properties? And we've started to think about the properties of swarming, from robustness to scalability to adaptability, how humans interact with swarms, and how we can test them in a more engineering sense to gain confidence in what the swarm is doing. From the properties perspective, if you think of a swarm being robust, scalable, adaptable, that sounds really trustworthy. But if you drill in, if your system is robust, that means some agents are failing. Do you still trust the system? Maybe if it still completes the task, but maybe you're bothered by that failure. If the system scales, in theory, that should be more trustworthy. But all of a sudden, you have lots of robots that you have trouble wrapping your head around. If your system is adaptable and so continues to work, in theory, that should be more trustworthy. But wait a minute, the behavior of your swarm changes all the time. And so there's a fundamental piece of work to do in understanding, do people like this because it delivers, or are people worried about it because it has different aspects that make it harder to wrap your head around? Human swarm interaction side, can we give control to people? And this is work by James Wilson, to give them basically to choose what they find makes a system more trustworthy. So with the cloakroom, they might choose to make a safe cloakroom because people keep walking in it. Or they might one that works very fast, or is robust, or is greener. And can we allow people to choose those things? And then we evolve, using map elites, different solutions, basically a spread of solutions people can choose for that optimize the trade-offs for these different characteristics. When people look at swarms, what do they think? And so here you're looking at human trials we recently did with 20 users. This is our lab-based cloakroom. They deposited objects, for example, a cell phone. And there's two behaviors here on the left, which is more organic motion. So it looks a little bit messier, not very straight angles, but it delivers just as fast as this structured motion, where everything is very mechanical, goes as right angles. And so we've been asking people, which one do they trust more? We usually give them only one condition so that they're not biased by looking at both videos, and we're still processing the data. But this is something where if people embrace maybe how organic systems can operate within their everyday environments, maybe they don't need to look so mechanical. Turns out that preliminary data doesn't seem to show a big difference between how they feel about the organic motion or the structured motion. And a little bit like engineered airplanes, we've been thinking about how we specify, verify, and validate these emergent properties of swarm behaviors. So this is a framework taken from the machine learning community, which has a similar issue. How do you go about specifying for systems that learn? Here it's how do you go about specifying for systems that have emergent properties. So we have adopted this framework now called EROS. And that allows us to specify things we care about. So for example, for the cloakroom scenario, we really cared about not blocking the fire exit. That's an emergent behavior because you need multiple robots to end up in the wrong place for that fire exit to be blocked. And then based on those specifications, you can do formal models, you can do low fidelity simulations, which allows you to do lots and lots of tests. You can do high fidelity simulations, and that code from high fidelity translates directly to our robots. So you can also go ahead and test the real robots in the arena. The red area is the fire exit. Turns out it's a bad swarm behavior because they do end up in that fire exit very, very often, which is something that I've learned since is a problem. And so you'd go back as the engineer and change your swarm behavior for the desired swarm specifications that you care about. And then if things do wrong, can you find errors and fix them? So here a swarm of 4 robots is trying to carry a big box, and that red robot is faulty. And that red faulty robot is hindering the ability to carry that very large box. And so what we need to do is figure out ways in which the robots can detect that. So we have ways in which, using only onboard information, robots know that they are faulty, and then mitigating that strategy so that it's able to perform its job. So for example, here, the bad robots go to the left of the arena based on onboard detection. And though it takes a bit longer to create a team, eventually they do manage to carry those objects. So one thing that was fun with the cloakroom scenario is when we told people, do you want to put a cell phone in our cloakroom or a scarf? They put cell phones. And we're like, why do you trust our cloakroom? And I said, I don't trust the cloakroom, I trust you, because the developers were right in front of them. And so there's a lot that goes into also creating teams of humans who care about how to design these swarms. So this is an older picture, but we're a big team of swarm engineers, and we also interface with a lot of different disciplines. For the students in the room, I guess it's fun to just think beyond engineering sometimes, social science, biology, chemistry, education. And to really think about how you also create human teams who create this technology, from embracing the great skills that we have, to nurturing interactions, to aiming for a common goal and hoping the right thing emerges. And so I'll stop here. These are some of the goals that we're aiming for. If you think of swarms, think of scale. And if you think of scale, then you can aim for big problems. And that could be the medical context, climate change, building things in space, logistics, farming, and construction. Okay? Thank you.
Thank you.
So any questions? There is one question.
So is there a possibility to use virtual numbers with the real robots to give them a complete population intelligence?
Yes.
Is that possible?
Yes, definitely. So for example, with the big drones, the first trials with the small aircrafts, the 3 in the air, we had 6 others virtually in the air with the real aircraft so that we could progressively move from the simulated world to the real world with digital agents as part of our twin environment. So that's one aspect of it. The other aspect is just in terms of trialing and learning and doing a lot on the simulated world before we translate to the real robots. That makes a lot of sense. So those robots pushing the Frisbee, all that is done in simulation on board. So they have virtual agents basically problem solve before we put it on the real hardware.
Thank you. That was very interesting. Just one question about when we were talking about trustworthiness and swarms. With that video you showed where there were the swarm operating in a more mechanical manner versus one in a more organic manner. Do you think in that type of context people would, because you said the preliminary data didn't show much of a difference. In my mind, I feel like I would, in that context, feel a bit more trustworthy of the one that's more mechanical because almost you can intuitively understand where it's going. It's going in a straight line, whereas you think, it's unpredictable. Of course, it may be like predictable in terms of like the rough what it's doing. But do you think, I know the data didn't show much difference, but what's your opinion on whether humans favor organic motion or sort of mechanical motion, or is it context dependent? And if so, sort of what context?
That's a great question. I think we don't know yet. From the human from the trials that we've done on use case studies, they want the system to work. And usually that's the thing that they care more about rather than understanding how it got to that working point. So I'm not sure yet, but it's a bit reassuring that they weren't very worried about the more organic approach. And then there's also a question of how we perceive these systems. If we perceive them in a more organic way, they're a little bit more like your pets, like things that work in your environment that you don't need to be perfect. And that somehow that sets a level of expectation that might actually work really well for the real world, because you're no longer saying, oh, you didn't go in a straight line. You're like, oh, I hope it finds the jacket. Like it's slightly different in terms of how you perceive what it's doing, because your expectation is different.
Yeah, nurture the robot.
I don't know. When we show these to kids, they look at our mechanical robots with like metal legs, and they're like, oh, it's doing that. I don't know. There's something creature-like about it.
Interesting. Yeah.
Thank you. I guess we have one more question here.
Thank you for the presentation very much. And we are also working on the drone swarms, actually finally to reach some collaborative task. And I'm very interested in how do you set up the communication schemes between these agents, between these swarms. And I found one of the, I have a dynamic picture there. There is, it seems that the link is very dynamic. Can you give me some more details about
for the ground ones, or
for the demonstration ones, for the colorful points, the colorful circle points, yeah, that one.
Yeah.
And I see that the link is very dynamic, so I'm not sure which kind of topology you are using to communicate between these agents.
Mm-hmm. So communication is one of the challenges that we face. It's often the thing that we hit a wall against. So for the drones, for example, being able to do long-range communication is quite challenging. So sometimes we won't do peer-to-peer. We'll do via satellite or 5G or something else. Or we have large, so the latest trials had very long-range radio, basically, to be able to communicate from the drones. The smaller aircrafts that I had during my PhD was Wi-Fi dongles, but they could communicate within 100, 200 meters. And then the ground-based robots, what you saw was a simulation with those links breaking and not breaking, but on board the robots we have Bluetooth, Wi-Fi, and then 5G as well that we can change. So we tweak, basically.
Yeah, so in general it's just about the distance between the
For that simulation it was distance-based.
Okay, thank you.
Yeah.
So thank you very much again. We have the break now, so feel free to have a drink or biscuits, and we will be back at 2:15. Yes, thank you. I think we are ready to start the last session. So, should we start? So our next speaker is Professor Damien Coyle from University of Bath, and the title of the talk is Neurotechnology, Brain-Computer Interfaces and Human Augmentation Technologies.
Thank you. How are we doing, everyone? Nice to be here to talk to you. You can hear me okay, yeah? Okay, good. Yeah, I've already said what I'm going to talk about. So I'm going to talk about neurotechnology and its various applications. I don't know if you're familiar, anybody familiar with brain-computer interfaces and neurotechnology? Anybody interested in this? Yeah, okay. Hopefully by the end of the talk you'll all know a little bit more about it and be interested in it as well. So it's been associated with a number of different applications. Some are deployed, but mainly it's in a research context. So you've got medical applications, assistive technologies, rehabilitation, gaming, and even used in the workforce and so on. So I'm going to talk about some of the end users that I've focused on over the last while, and I'm going to introduce the technology and how it works, whilst also talking about the impact on these individuals, people with spinal injury, people with post-traumatic stress disorder, people with stroke, people with brain injuries. So how does a brain-computer interface work? I'm going to tell you a little bit about that. We normally use motor imagery, which is imagining movement. So you imagine your movement of the arms, and you can modulate signals in the sensory motor area. So when I do a right arm movement, I'll see changes happening on the left side. Left arm movement, changes on the right side. Foot movement will be in the center. Tongue movement is here. So we know quite well spatially where things will change. And we know what happens whenever they change. At a resting state, you might see the slow rhythm called a new rhythm. Whenever they do the movement, that rhythm disappears and you get a higher frequency component. So that's what we're kind of looking for when we try to decode brain-computer or brain activity. Okay, so why motor imagery? Well, as I said, it's spatially well defined, so we know where to look for it. It's also spectrally well defined. It's also a skill that you can learn. So whenever you learn to grasp a toy as a child, that was you training your motor cortex to learn that function. In a brain-computer interface, you can train your motor cortex to modulate signals that we can pick up with electrodes placed on the scalp. And so that's one of the reasons why we use it. It also makes sense if you're going to control something to use movement-related control structures. I also want to emphasize that it's a learned skill, so you can learn to get better at controlling a brain-computer interface over time through feedback and through learning. And there's normally three things associated with that. That is user engagement and training, machine learning, and then the application is key as well, because you can only learn or train for so long without having an end goal. So you want to have something to achieve, and so what you're applying is probably going to be very important. So even though we know spatially and spectrally where signals change, we also have to do a lot of AI, and I'm not going to talk about that in great detail today, but basically you take the signals and you feed them through multi-stages of signal processing, and what you want to achieve is a signal that goes one way for left arm movement and the other way for the right arm movement, so just changes in polarity. And if we can do that, we normally set a person down and we ask them to imagine movements corresponding to the left and right arrow here. So we collect data to calibrate a system that can translate the information. And then we can set thresholds on the outputs of that system. So whenever I do a right arm movement, things should go towards 1. Left arm movement go towards -1. And it normally takes a second or two for that to modulate. And so you can see the Q here is at 3 seconds, which is quite important. If I want then to measure how accurate that is, I'll look at multiple trials. So we get somebody to do 50 lefts, 50 rights. And we classify it before they begin. So you should get around 50% accuracy in that period. Whenever they begin the imagine movement, it goes towards a peak in terms of the accuracy that we can distinguish those 50 lefts and 50 rights. And we want to show that the baseline versus peak is significant and there's an improvement. And then if we do permutation tests, we also look at the frequency components and see if there's a corresponding frequency response. So that's a very quick crash course in how that operates. I showed you a nice control signal there that went up for left and down for right. That's not how it operates in reality. You've got a lot of this jitter, a lot of biasing towards one or other class. And you can see here that the square wave is the target, right? So that's do a left arm movement, do nothing, do a right arm movement, do nothing. And so that's what you're trying to follow. So you have to do a lot of post-processing on the signal. So we do debiasing, smoothing, multiple thresholding, and eventually we start to follow what we're meant to be doing. And that's the whole process there. And so the idea here when you do brain-computer interface is that you get better over time. So if I put a headset on you today and asked you to do imagine movement, I might be able to distinguish with 60–70% reliability between left versus right. Some people might get a little bit better, some people a little bit less. But then over time, as I give you feedback, you'll get better at doing this. And this might be something that you would see in a feedback scenario. So here we've got 32 channels of EEG. This is our control signal here, you can see. So that's the translated signal. And that's linked to the position of this neuron character in the game. And so when a light appears on the left, the person has to imagine left arm movement to move the character to the left. And when the light appears on the right arm movement to move it to the right. And so even though they're playing a game here, we can collect data within this game as well because we're dictating which command the person should do. And there's a timing associated with that as well, okay? And we could hook that up to things like robots, and this is not playing now. Let me see. Okay, so this is a robot, but here you can see the feedback signal at the top, and the robot has to make a decision at each junction. So it follows the pathway normally. Whenever it becomes to a junction, the person has to do imagine left or right arm movement, and then command the robot to go in the right direction. So you've got a shared control strategy between the brain-computer interface and the robot in that scenario. Sorry, I couldn't play the video there, but we can see that. And if we do self-paced, so if we move to the junction with the robot and you have to wait a few seconds and then do a left versus right, it's much slower than having a self-paced scenario where the person can continually modulate brain activity and control the robot. So moving on, I think, can you play both of these videos on the left, please? Yeah. So this is a competition called Cybathlon where spinal injured people compete against each other, controlling virtual races with their brain activity. There's other races as well which are more physical. There's a functional electrical stimulation bike race, there's a powered wheelchair race, there's a robotic exoskeleton race and so on. But the idea is that people with physical disabilities can compete on an international scale in this competition. And so you see here the brain-computer interface race. You've got a vehicle in the middle of the track. The pilots have to turn the vehicle left, right, turn on the lights, and then have a no control state. So this is more complicated than doing left versus right. It's difficult even to detect the no control state because you can get a lot of false positives, a lot of false commands. And so we've got a load of different strategies for this. Quite a lot of signal processing goes on. Here we've got 4 classifiers happening. So you've got left versus right, left versus feet, feet versus right, and task versus relax. So you have 4 classifiers operating in parallel, and then you've got decision-making mechanisms, timers and whatnot to make sure that you get the right command at the right time and enable the pilot to control the race. So this is us in Graz in 2019. You can see the race time is basically your performance metric here. So you can see race times coming down in 2019 and also coming down in 2020 when we competed again. But just a few days before the race, time started to go a bit pear-shaped. And we were wondering what the issue was here. Was it our algorithms? Probably our algorithms were not picking up changes in the pilot's effective state. The pilot was coming to Zurich, coming to Graz, eating a different diet. So, you know, and also may have had competition day pressure. So that type of thing is very difficult to deal with when you're dealing with non-invasively recorded brain activity. So then this year we competed in 2024, but they made it a lot more difficult. So this time you had to steer a wheelchair through a virtual environment, move an ice cube collecting cup into an ice cube machine, put a key in a keyhole, and control various things. So that, again, lots of control in this. And we came first in this competition in 2024. That was at BCI Challenges. There's another event in Zurich. But what did we change? Well, we had to change a lot, the signal processing strategy, and change to match that paradigm. We're not going to disclose that because we're competing against in Zurich now in a few months' time. We'll let you know all about it after. But we also had a sports psychologist work with Owen and regulating his brain or his breathing and looking at getting into that zone, that relaxed state. So I think that was quite helpful as well and very important. People who do meditation typically do well at brain-computer interfaces, people that can relax and self-regulate. Sorry, that was just some of the could you play this one on the right as well, please? Sorry, that's the, yeah. So this is kind of the wheelchair control. You have different strategies there, so I'm going to move on. So this was left versus right, you know, very distinct areas. What if we could decode three-dimensional movement, so pointing in three different directions? This is much more difficult, but what we've been able to do is put people in a VR and get them to point to virtual targets multiple times. Then we measure the trajectory, and then we ask them to imagine pointing to those targets. All the time they're wearing an EEG cap, so we're measuring their brain activity. And then we try to map or decode those signals automatically by measuring brain activity. So you can see during the movements, so you've got a home, and then target, and then home again. You can see oscillations here in the, you know, around 8 to 10, 12 hertz. And so this information can be detected and measured, and we can use various other signal processing tools. So here we're using LSTM, long-term, short-term memory, and convolutional neural networks. So convolutional neural networks will find the features. LSTM will combine them temporally to enable us to potentially decode in those three different directions. Everybody probably knows about hyperparameter analysis, but when you're dealing with neural nets, there's quite a lot. So we use high-performance computing. We use things like ASHA, which is an optimization tool that allows you to distribute jobs across different neural nets and home in on the best parameters quite quickly. So if you're not using HPC for deep learning, I would suggest you do that. The online framework then involves both Python and Simulink, MATLAB Simulink. So we do the real-time acquisition in MATLAB Simulink. Because MATLAB Simulink doesn't have good AI tools in general, we have to then send it out to Python, and that communicates then with the feedback in the VR paradigm. And so what we wanted to do was to see, was it worth the effort of putting VR on people? Was the embodiment and immersion better than a 2D screen for decoding three-dimensional movements of the hands? And what we found was that with 2D, the correlation between the target trajectory and the actual trajectory, or the imagined decoded trajectory, is lower when compared to VR. So we're quite confident that VR did help this scenario. And this person was able to, or that the subjects in this study or participants in this study were able to do around about 70% correlation in terms of decoding three-dimensional movement, which is an achievement for non-invasively recorded signals. And we're quite confident that this merger of brain-computer interface technology and VR and other kind of immersive tools will be quite important in the future. So we also look at trying to decode lower limb movements, so stepping in a lower limb scenario, and where we measure different points on the legs, and we ask people to step and return step. So you could see here, this is kind of the step forward, step back, and do that multiple times, and loads of different trials and so on to do this. Again, we're applying that similar framework, but we also compared it to a more traditional multilinear regression. So this is another way of decoding temporal information. We compared that to the CNN and LSTM framework. So you can see here there is differences in different markers whenever we do the step. So pre-task, and then you can see, so that there is information in the event-related spectral perturbation that we can use to potentially decode stepping. And what we were able to show across multiple participants was that, first of all, CNN LSTM was better than multilinear regression. So again, that deep learning framework giving us an advantage. But also that the correlation is quite high, especially for that, where the gross movement is, but less so for the left and right. So yeah, so totally decodable. And the idea is, so they're just more examples of this is kind of the stepping and different, and then the target versus actual. So what do we want to do with this type of technology? Well, it's mainly focused on, can we improve robotic assisted gait therapy using exoskeletons? Can we decode a person's intention to move? Can we decode a person's intended gait? So these are all very challenging things to do in real time, but the early results shows that is possible. So we have to hook this up with an exoskeleton. Could you play both of these videos, please? And so here we basically have a brain-computer interface, somebody wearing an EEG cap, and I don't know if you're familiar with the Exobionics exoskeleton. It'll hold your full torso up, and it'll either do actuated steps automatically, or initiated by the user, or assisted gait basically. And so what we found is that, well, here the person has to imagine the movement or attempt the movement. We detect that, and then we send a signal to the robot to initiate the steps. If a person was in that passively without a brain-computer interface, the effect that has for rehabilitation after stroke, for example, is less than when they have to engage the brain first, so it makes them really focus. If somebody's doing therapy with you, and you're not engaged in the therapy, it won't be near as effective as a therapy where you're actively engaged. And brain-computer interfaces make people actively engaged, because you first of all have to actuate a part of the brain, and then we detect that, and the whole sensory motor loop is engaged then. So yeah, this is quite important, and I think we'll keep progressing this. A lot of work going just to get that interface going. Here we're not doing three-dimensional decoding, we're just detecting attention or intention to move. To translate that in the three-dimensional decoding into the whole gait cycle will be another step. Yeah. So again, quite a lot going on in the signal processing there. And yeah, quite a lot going on in the control algorithm. Basically these robots have to detect a left lean, and then you do the right, and a right lean, do the left. And so yeah, quite a bit to do within that. But just so you know, the BCI offers a completely different alternative for rehabilitation after physical disability caused by stroke, whatever. And a number of meta-analyses have shown that active engagement of the brain through a brain-computer interface can indeed enhance rehabilitation outcomes. So I also mentioned another study earlier. This is prolonged disorder consciousness. Now, I don't want to go into any great depth here, but basically people who have a brain injury may come through a coma. They could be diagnosed vegetative or unresponsive wakefulness syndrome, UWS. And in UWS, you're completely awake but assumed to have no cognitive awareness whatsoever. In minimally conscious state, you're assumed to be awake but have fluctuating consciousness at a minimum level. In locked-in syndrome is where you're fully cognitively intact but just cannot move to communicate. And so there's a lot of difficulty in determining what state a person's in if they have no consistent behavioral response. Some people don't even have a reliable eye blink and so on. And the traditional assessments kind of depend on a behavioral response, an overt behavioral response. So if an assessor doesn't see that, then that person could be, diagnosed vegetative and, put in the corner and maybe not get the stimulation they need and so on. So we wanted to develop a movement-independent response, which is, again, using a brain-computer interface. So we put a hat on the person, we asked them to imagine movements, and we try to determine, can we distinguish between left and right arm movements in these individuals? And then we've entered them into a training program where we follow them for 10 weeks, 10 sessions. And in those sessions, they get real-time feedback. Now, these patients close their eyes during the experiment, so rather than giving them the visual feedback that I showed you, we give them auditory feedback, so we're moving sounds. And we have some musical sounds in there and various things. And then at the end of that, we have a number of sessions of closed Q&A, closed questions, basically, where we know the yes/no responses. We sit with a family member, and we determine what responses they have. Or the correct yes and no responses. And we ask the family member to read the questions aloud, and then we record them, and then we play them back repetitively to the individual, and they have to respond by imagining movement. So what we're able to show is that with a brain-computer interface, the difference between these groups is not that different, right? So people that are diagnosed vegetative are not that different, not significantly different to MCS when we use a brain-computer interface. But when we use the behavioral skills, they are, the overt behavioral responses. So it's shown that even people in those very, assumed to be unaware are able to modulate brain activity. Now, we've done about 45 patients in this, so the Q&A results are still a bit low in terms of the number of people we've engaged with, the number of sessions we've done. But we split those questions up into biographical awareness questions, situational awareness questions, logic questions. And so what we're able to do is to see if there's differences in their cognitive abilities in these states if we determine that they're aware. So yeah, quite important, a large trial ongoing with about 17 hospitals. We've also used kind of different type of technology. It's called neurofeedback. So we ask people to self-regulate or down-regulate, up-regulate specific rhythms. And we get them to play games like this. Well, they don't actually play the game. They just have to produce the right rhythm, and the game will operate normally. If they don't produce the right frequency band, then the game will malfunction and so on. And so here they're asked to down-regulate alpha. And we did this with 30 participants in Rwanda, where there's a high prevalence of PTSD. And so basically, the participants that got the alpha down regulation treatment actually showed an alpha rebound. So typically, people with PTSD have a lower resting state alpha, and you want to increase that. So it kind of doesn't really make sense to down regulate it, but when you down regulate it, you get an alpha rebound, which is higher than the resting state, and that has the impact on default mode network and so on. So yeah, the PTSD group showed significant signs of reduced symptoms after 7 or 8 sessions of this treatment. So yeah, quite a important outcome for that type of technology. Interestingly, we had a control where they just did motor imagery, so that's imagining movement. It wasn't intentional down-regulation, and they didn't have the same effects. So there is something about down-regulating alpha in that specific region. Okay. So I'm going to briefly go through a few others there. I don't know how much time we've left, but this is different types of BCI. So I've been talking about either neurofeedback or motor imagery type BCIs, but there's also event-related potential BCIs. So when you view a stimulus, and depending on the content of that stimulus, where it's located and so on, you'll get different potentials that occur 100 milliseconds, 200 milliseconds. So for example, the P300 is a positive potential that occurs 300 milliseconds after the person engages or sees a response. Okay, so here we have what we call motion onset visual evoked potentials, and within this, I don't know if you can see these stimuli, that top one, but basically stimulus are moving from right to left here at the top of this game, and whenever a stimulus moves from right to left, you can see that there's activation on the left side over occipital areas. and depending on when that stimulus occurs and which one the person's looking at, we can decode their intention in terms of the direction of this car. So they have 5 different lanes here. Okay. I'll now talk about the signal processing here. So here's another type of thing. Is there anything different in the stimuli here? Is there one specific stimuli that stands out to you? Snake, yeah. So the snake is like a threat, right? So in this study, what we wanted to do was determine, could we detect threats versus non-threats by looking at the brain response? And we presented first-person threats where it feels a bit more threatening when it's first person. Then you have faces and angry or sad or whatever, and objects or scenes. And what we were able to show that within 100 to 175 milliseconds, we can detect the difference between a threat and a non-threat just by looking at the brain response with about 70% accuracy. If we use a little bit longer time, then it gets more accurate and more accurate. And that the personal threat or that first-person threat, like the snake in your face, is more easily detected than, say, an angry face or a scene that seems threatening. Okay. And so what we wanted to do was hook that up to a paradigm then. So we had 28 participants in that previous study. So here the zombie is the threat, and we were able to detect in real time. So you could actually respond to the threat by looking at the brain response. Either put up a shield or whatever it might be. But if you had to physically react to that threat, with some kind of movement-related response, that could take over a second, whereas this could happen within 200 milliseconds. Although I wouldn't do anything that's safety critical with this, because when you go online with these things, it's very difficult to manage some of the oscillations. So there are other signals: rapid error correction. You looking at error-related potentials, looking at advanced braking, where you could detect the intention to move before the physical movement, so you can speed things up. And if we take all this together, there's a lot of advantages that you can gain from measuring brain activity in terms of time and latency and response. And you could actually give gamers, for example, an advantage to respond to certain things within environments. So yeah, lots of potential there, although as I say, it's very difficult to do this because brain signals are very non-stationary. All these things cause challenges, and that's why brain-computer interfaces aren't everywhere, because they're not robust enough yet, and we're working on better ways to do this. This thing around non-stationarity and covariate shift is a big problem, like it is in many applications. So we need hundreds of people, thousands of hours, and to get more data. And I think I'll wrap it up there. So we are creating new technologies to enable this. And the UK is really focused on neurotechnology in general. There's regulatory activity going on, and there's a lot of preparation for how these technologies are going to impact on society. I'll leave it there then. I think we're all out of time, are we? Yeah.
Thank you very much.
Yep. Thank you.
Any questions? We have.
Thank you very much. Yeah, I've got a question about the vegetative state, the experiments you were running on individuals who had been diagnosed as being in a persistent vegetative state. Would you say that the work that you did, although you said that it was somewhat preliminary, does that demonstrate that our current methods for diagnosing vegetative state are just completely inadequate? Because once someone's diagnosed as in persistent vegetative state, there's effectively, as far as I'm aware, there isn't much sort of, as you sort of said, there isn't much sort of treatment plan that would be sort of proposed from that. Whereas if this research is showing that actually there is some kind of awareness there, then I guess the traditional methods are effectively shown to be, I don't want to say useless, but if they don't adequately sort of reliably detect whether someone is truly in a vegetative state or whether they just can't interact with the world enough for traditional methods of analyzing their behavior to determine that, then yeah, would you say that?
Well, first of all, vegetative state is a term that people don't use as much anymore, because there is that awareness that people are possibly aware in those states. There's a lot of subjectiveness around how we assess with behavioral response. A lot of it is people assessing somebody, follow this, shake maracas around their head. There's standard techniques there, and they are relatively reliable if you can get consistent and overt responses, but they're subject to failure as well. So I would say yes, there is an upgrade needed. But unresponsive wakefulness syndrome is now a more accepted term. Motor disassociation is a more accepted term. And in the US, there is a lot of regulation now to say we can use neuroimaging, MRI, EEG to add value to clinicians' assessment protocols. So I think there's a lot of movement in the right direction. But yeah, I think it's very necessary to do that. So your question really was around what can we do for these patients afterwards then? Because if this technology could be used to enable them to communicate, that would be excellent. Now that's a big leap. But even in the experiments that we're doing, even that engagement with the patient and getting them to do something, either modulate their brain activity to move sounds, move musical sounds, is very therapeutic as far as we're aware as well.
So would you say that that's kind of almost on the horizon as a future goal, to be able to almost provide these patients the ability to interact with the world again?
Oh, for sure, yeah. That is, over 12 sessions we can show, although the accuracy is lower than your typical participant, we can show accuracy going up. And we're making really easy to use technologies where you could have it at the bedside. The family member or the clinician can put the headset on, have a tablet there. They can go away and come back after half an hour. The person has engaged through what they were meant to do, and you've got data on how they engaged and so on. So yeah, hopefully that will all come about ASAP. Yeah.
Sounds very exciting for the future.
I guess we can. We have Manoush there, and then one.
Is it possible to recover the full weight from a set of stimulation?
Sorry?
Is it possible to do the backward? You have certain stimulation and you recover the weight from expected from your device.
Well, there is a lot of effort ongoing to try and decode visual information from what a person sees from the brain. Is that what you mean? Yeah.
I mean the opposite. So basically, you have a set of sensors in here that will produce a signal, a full waveform signal. You translate that to motion or a stimulation. Yeah.
Yeah.
So I want to go backward. I want to just observe the stimulation here. How can I produce the full waveform?
Yeah, we have some studies ongoing with that. Robert Clark in our department there is doing something on that, and there is evidence that you can decode some of that. Yeah, for sure.
I guess we have one final question from online audience.
There's a question online. I'll just read it. You mentioned how a person can get better at using a BCI over time with practice. Would someone that had previously only used a BCI for arm movement get better at using a BCI to detect leg movement?
Yeah, probably, because the four movements that we use, tongue, hands, feet, are very well defined spatially, and that's why we use those four. If you go beyond that for individual limb movements, it's probably difficult to decode. Finger movement you can't decode non-invasively from brain activity. But if you've been able to learn to modulate activity associated with left versus hand movement, or left versus right hand movement, then the assumption is that you'd be able to learn to modulate activity with leg movement, limb movement. Yep.
So thank you very much again.
Okay, thank you.
Our next speaker is Stephen James from Dyson, not the institute, the company. And he's going to talk about robot learning for advanced domestic robotics.
Oh dear, I'm not sure what's happened to my slides. That bottom half is a bit strange. Okay, yeah, hello everyone. So I lead the Dyson Robot Learning Lab in London. This is a new lab that opened January of last year. And before I dive in, I kind of want to just dissect this title a little bit. So robot learning, first of all. What do I mean by robot learning? Yeah, I think my slide formattings are a bit weird. So what do I mean by this? Well, I think the best way to describe robot learning is to actually look at how we do robotics, or how we've traditionally done robotics. So what you would normally have in a robotic system is you'd have some observation come in, maybe some RGB data, and then you'd kind of do a scene understanding phase. You model the world. So for example, let's say we wanted to interact with this bottle here. We'd do object detection, right? So we'd have a system running that detects items, in this case, bottles. And once we know, what that object is, we then want to know where in the world is it. So we know what it is. We need to understand where it is in the world. So once we have that, we know where it is. We want to be able to then plan how we're going to interact with that. Where's the best place to grasp it? What am I going to do with it next? Once we've planned where we want to grasp it and interact with it, we need to do a planning stage then to how am I going to get my arm that I want to interact with this object over to the bottle. And then once you finally have that plan, you then operate some sort of control process to bring, to follow that motion, to follow that plan, and bring your robot to that object you want to interact with. So it's quite a lengthy process. Each of these individual components have entire fields in themselves, and some of them has dedicated conferences and workshops to them. So it's a very kind of complex system. So what robot learning tries to do, or a lot of robot learning work, is that it tries to simplify the entire process and directly map observations to control. And then we stick a neural network or a series of neural networks in the middle. So the idea is that we're offloading the complexity of this system, this larger system, to the neural network. And it can represent that world. It can do the scene understanding phase however it wants. It may do it in a very similar manner as to how we currently do it today, but we just don't know. It's up to the network to decide. And then finally, this advanced domestic robotics. What do I mean by that? So I mean tasks that we do every day in the home. These are chores that we do, and they often require complex manipulation in the world, complex dexterous manipulation. So these are the sorts of things that we're interested in. And so our research in the lab can be kind of summarized with these 2 points. So demonstrations. We collect the demonstrations, so we want to show the robot what to do. Let's say we wanted to grasp this bottle, going back to my example. We would actually show it examples via a human of how it could grasp it. And we would record the observation data, for example, the images, and then we'd also record the joint kind of velocities, for example, or the end effector pose of the arm, and then we would basically teach it to mimic very similar behaviors as a human. And then we would also, what we're also interested in is then adding in this exploration component. So this is reinforcement learning. So the one on the left is imitation learning, and then the one on the right is reinforcement learning, right? So we can kind of take this agent that has been kind of bootstrapped with these demonstrations, and then we can let it explore in the world and learn from its mistakes. So left is showing the robot what to do, right is letting it learn from mistakes. And so really, the goal of our lab within this domain then is to maximize robot capability, so what we can do with the robot, but reducing the sample, increasing sample fit, but reducing the samples that we need. And that's really, really important because we don't want people collecting thousands and thousands of demonstrations on a daily basis, right? We want to do this as efficiently as possible. So here are some projects within this area that I'm going to talk about today. The first one is end effector redundancy. And so in robot learning, it's important to understand that there are 2 main ways to control the robot, right? And what I mean by this is that we have a neural network taking in some observations and then predicting some output, right? And this output can either be end effector controls, or it can be joint controls. Oh dear. very bad formatting. Okay, so if we take a look at these graphs here, these are learning curves, what we call learning curves in reinforcement learning. The y-axis is showing success, and then the x-axis is showing environment steps, how many times we've interacted with the world. You can kind of think of this as time if you want, but generally it's how many times we've actually acted in the world. And so what we really want is graphs that look like these kind of orange ones, right? So we want to, as quickly as possible, get a high success rate. And end effector space gives us that. So in certain tasks, for example, taking lid off saucepan and stacking wine, we can actually get high success rate rather quickly. But joint space is slower, as you can see. But then if we have certain tasks that require much more full control configuration of full control of the arm, so we need full joint configuration. So for example, we've got this kind of take bottle out of fridge task, which looks something like this. So you imagine you've got this fridge that's slightly ajar. We really need to control every single joint to kind of get right in that fridge. If we're just controlling the end effector, and we've got a high degree of freedom arm, which in this case we do, this is 7 degrees of freedom, then we've got that redundancy, which means that for every single place that the end effector can go, there's actually multiple solutions. And so what can often happen is that the robot will knock the fridge. So what you get then is the opposite, where it's still inefficient, but at least it can do the tasks, whereas end effector control doesn't. And so in summary, end effector space, it gives you the sample efficiency, right? It's pretty good here, but we only get partial arm control. We don't have full control of the joints. Whereas with the other action mode, it's the opposite. So we get that full control, but it's normally sample inefficient. So here's a concrete example, just to kind of ground everything I'm trying to say. So the goal is for the robots to go into this cupboard here and grasp a wine glass and then put it on the top. And this is using end effector control. So we've taught the robot using end effector control, and it's not able to do the task. Whereas if we were using joint control, it has full control, and it can bend its elbow down and go into the gap. So in this work, what we did, we introduced a new action mode to control the robot. And the kind of action mode family is end effector redundancy, or ER. And there's a few different ways that you can achieve ER. ER joint, or ERJ, is one of these. And the idea basically is to remove the redundancy. So we kind of do this hybrid where we want to get to 6 degrees of freedom. So we lose that redundancy, and it means that every single time we predict an end effector pose, there's only one solution to that. So that means the network gets full control over the configuration. And so we want to remove end joints. So for a 7 degree of freedom arm, which is the very common set of arms that you get today, it means we want to remove one joint. So what we do is we get the network to predict that one joint. So we do joint control for one joint, and then we do end effector control for the rest, right? And so that means that we do 6 joints with end effector control. And then this is what we get when we do that. So as I said, this was ERJ, and you can see that it means that we can do more tasks now, and more complex tasks, whereas other methods, in particular end effector, are not able to achieve it, and joint control can achieve it, because of course that's like the most expressive, right? Controlling every single joint, but it's, as I said before, much less sample efficient. And here's just some examples here. So ERJ, task, is just another name for end effector control. Okay, and this is quite an obvious example where we want to control the elbow to press a button. With task space, this is impossible pretty much with a 7 degree freedom arm, because it's only controlling the end effector and has no way to actually control this elbow joint. And then finally, kind of tight, confined spaces, we're able to kind of go around objects without knocking anything using ERJ. OK. So next up is render and diffuse. So everyone, I'm sure, is very familiar with diffusion or image diffusion. So if you've used ChatGPT, you've likely come across OpenAI. OpenAI have also released the DALL-E series, which is currently on DALL-E 3. And this is image generation. So you give some text input, and it then generates you an image. But what's actually happening in the background is that it starts with noise, like this blurred image, and it's the kind of diffusion process denoises these images into something that then looks something like we all recognize. Why I'm talking about this is because this concept has been applied to robotics. So this is work from Stanford, I believe, where you operate at the end effector level, and you're starting with noise of potential places that your end effector could be, a trajectory, a noisy trajectory, and then you're denoising through a diffusion process. And this is kind of how this looks, the current system looks, of that last video. So you take an input image, and then you start with your noisy actions, right? So let's assume that we're using joint positions as the actions. So we take in the joint positions, we take in the current image, and then we have a neural network that predicts the denoising action. We then apply that denoising action to the noisy action, and then we get a less noisy action, and then we repeat the process. This is what the diffusion process looks like. But the problem here is that you're not just diffusing. You're not just trying to understand the semantics of the task. You're not just trying to understand trajectories. You're also doing this space mapping as well. You've got an image space coming in, and you've got a joint configuration space, and you're trying to predict a joint configuration, in-joint configuration space. And so what we want to do is take off, loosen some of the responsibility that the network has to do, and it can just focus on what the task is. And so instead what we do is that we represent the actions, the noisy actions, inside the image. So now we don't pass in an image and an action. We actually just passing an image with the actions drawn in. So what that means now is that we're going from image space, and we're also predicting image space, because our output also is which direction we're shifting those pixels. So now the network just has to focus on the denoising process, and it doesn't have to learn this space mapping. And this is what the process looks like. You can see that far left image changing as we denoise. And this is what this looks like in practice. And here's another example of sweeping some coffee beans. And then we also run this across a host of other tasks as well, including putting the toilet seat down, lifting some lids, sweeping coffee beans, putting an apple in a drawer, and opening a drawer and closing a drawer. And I should mention this is all real time as well. So I mentioned before we care a lot about sample efficiency. And this kind of helps us towards that, right? So if we look on the far left of these graphs, the highlighted area, this is kind of the Goldilocks zone, because we want to reduce the number of demonstrations as much as possible while getting a high success rate. And so, of course, as you keep giving more and more demonstrations, competing methods all start to then perform the same. But in this low data regime, there's actually quite a big difference between existing methods, state-of-the-art methods, and R&D. Okay, how am I doing for time? Okay, and finally, we have this work called hierarchical diffusion policies. So what I showed previously, it's really great for shorter horizon tasks. So maybe just picking up something or pushing something. But let's say we want to do many, many tasks in a single neural network. And let's say we want those tasks are very, very long. They're very, very long sequences of tasks, like load an entire dishwasher, for example. And we want to add in language in there as well, where we can actually talk to our robot. Now, if we use what I just talked about before, that's a lot for the network to have to do, right? And so what we're interested in methods where we can kind of start to impose some sort of hierarchy to break up the problem a little bit more. And so there's this popular paradigm that's emerging called next best pose. There's many different instantiations that have come out recently of this, but the high-level concept is this, is that we pass in our observations. So again, this can be RGB or depth data or other, and an optional language command. We then have a high-level agent. So this is a learned high-level agent that predicts the next best pose. What that means is you can kind of think of it as a point of interest. Where next in my kind of 3D world is the most interesting place for me to go to next? So we have this high-level agent that outputs this next best pose, and then we pass that to a lower-level agent. And then this can be whatever you like, really. But all of the literature so far has used motion planners for this. So you get out a waypoint in the world, and then you are applying a traditional motion planner. So in HDP, what we did is that we looked at replacing this motion planner with a diffusion policy. There's a bit more to it than just that, but in the interest of time, I won't be able to go into it. Just ping me after if you're interested in the paper. So this is what this looks like. So remember, we've got the next best pose coming out, and then we are applying a diffusion policy to get to that next best pose. And then this is what that looks like, a visualization of that. And here's a real-world example. So the nice thing about this is that now we've replaced that low-level agent from a motion planner to a learned control agent. That means that we can do more complex tasks, such as dealing with articulated objects, which is actually very, very difficult to do with motion planning. What you have to do in that case is actually start to hand engineer a bunch of things. Like you have to understand where the joint is, so you're able to understand like how you're going to manipulate with an object. Whereas now that we've replaced it with a fully learned agent, it just learns from data now. So we just show it some demonstrations of it doing the task, and then it'll just learn to understand and model the world however it likes. And then here's a kind of more beefy example. Again, I told you that this can take, these next best pose agents can take in language. So here's an example with language, where we're able to actually communicate with it. For example, open the drawer, put the teddy in it, and it's able to understand that and accomplish a series of kind of subtasks. And that brings me on to the final project then. And thank you very much for your time, and feel free to ping me for any questions.
Thank you very much. I guess we have a question here.
Thank you for the presentation. Have you considered about any formal definition of the sample efficiency? Because from the presentation, I see that only the empirical training process has been shown. Let me give you an example. If we think of some issue like local optima, if the training process is stuck at some of the local optima, and like, for example, 60%, because from your empirical training process, it's always finally, it looks very good, finally arrives at 100%. But in real applications, if we train the model and if we see that it seems to converge at like 60%, actually we are not sure whether it is stuck at one of the local optima, or we still need some more time waiting for more episodes to training. maybe it can reach some better global optima. So how can you deal with that? Thank you.
So I believe the question is about how do we know if there's more performance to be gained or not, or if we plateaued at, say, 60%. I would say that the way to know is that if you've been able to collect demonstrations in that, or if you can collect demonstrations, then you know that there is potentially more performance gain to add. What's perhaps happened here is that you just don't have enough demonstrations, right? So, or that the area in which you're collecting your demonstrations is not large enough. So a lot of these methods, they can interpolate, not all of them, but some of them, but they can't extrapolate currently. But once we hit that, then obviously all of the stuff I've talked about, the sorts of things you can do is just blows up then.
Thank you.
Yes.
I guess we have one more question over there.
Hello, many thanks for the presentation. I just wondering, because I can see there are many simulations in your presentation. I'm just wondering, have you used any of the sim to real transfer? And if you have you ever experienced the what they call reality gap? That you have the performance gap when you transfer the learned policies. And if you have, then how have you dealt with them? If you could share, yeah. Thank you.
Yes. Yes, so I'm very familiar with it. So a lot of my PhD was in this area of sim to real. And then towards the end, I became more interested in learning in the real world, simply because I'm a big believer that I think sim to real is, of course, part of the solution. But if you can get algorithms that are just incredibly sample efficient, then that's also going to benefit sim to real, right? Because it means that you're going to be able to train on more diversity and get even more general policies come out. So yes, I'm familiar with it, and I'm very interested in that area. And then particular applications of that, a very common way of doing it is domain randomization, which is where you kind of randomize simulation parameters. Another paper that I did a while back is about, it's called RCAN, randomized to canonical networks, and this is about putting like an abstraction layer in between, where you're mapping the real world into like a simulation world. So you're turning real images into sim images, and it means then that the agent feels at home, right? Because it was trained in a simulation environment, and you're turning real world images into simulation, and that's another way. But it's a big field, right? So there's quite a lot of work out there.
I guess we have time for one more question. Sabine here.
Thanks so much. That was very exciting. I wondered where the computation happens, both in terms of the training or
Yes.
or how can you put it at the edge?
So all of the training, most of the stuff we do is all on a single graphics card. I mean, we utilize many different many graphics cards for like the initial kind of experimentation, right? But then the final models that we can train and also run at inference are just on a single, say, 24 gigabyte graphics card. So, I mean, can it run on the edge? Yes, if you can afford to put a graphics card in your platform. But given the kind of progress of hardware, I assume it won't be long before we can put large models on the edge. Yeah,
okay, thank you.
In smaller units.
Thank you very much. So let's thank you, Stefan, again.
Yes. Thank you.
Next, we have Professor Andy Davison from Imperial College London, and the title is From SLAM to Spatial AI.
Okay, thank you. So I'll explain what that title means during the talk. Let's start with SLAM. So it's been mentioned once or twice already, but if you don't know what it is, it's simultaneous localization and mapping. It's the essential problem that a robot or other device faces if it wants to make a representation of the world that it's in, so that's mapping, and it wants to localize with respect to that representation, that's localization. And in SLAM, you're trying to do those two things at the same time. And I've, through most of my career, focused on doing SLAM using vision as the primary sensor. And my work goes right back into the 90s. But we had a particular kind of a breakthrough, I think, in about 20 years ago now, with being able to do this with a single camera. So I'll just very quickly show you a video of this. So this is what the algorithm we called monoslam. So the idea was just with a handheld camera moving through a space in real time connected to a single computer, can you get real-time estimate of the position of that camera in full 3D, and then can you build a representation or a map of the space that it's in? So the way that this worked, this is the view from the camera. We're detecting and tracking natural landmarks in the scene. So these are kind of point-like features in the scene that we can repeatedly track. And then from many, many measurements of their positions in the camera image, we're basically able to jointly estimate the motion of the camera and then the 3D position of those landmarks. So on the assumption here that these are static landmarks in the scene. So here we see a visualization of basically the output of that algorithm. So the real-time position estimate of the camera flying around, and the real-time, estimated positions of the landmarks that are making up the map. So you'll see that those kind of gradually converge to nice high-quality estimates. The ellipses you see are representing the uncertainty of the estimates in this system, and that's really the key to how this works. It's a probabilistic filter. We're taking lots and lots of observations from the camera and feeding them all into a probabilistic estimator. So that work has now really been the basis for lots of follow-on work, lots of implementations in companies, and it's really now out there in real products, this kind of stuff. So I've been particularly involved with Dyson, actually going back to just after that time when I met people like Charles Collis, who's over there, who were interested in developing new sorts of navigation and localization algorithms for robot vacuum cleaners, and we worked together on the project that ended up being Dyson's first robot product, the Dyson 360i. So this includes a vision system. So the bubble on the top you can see of this robot is an omnidirectional camera. That's where we get the name 360i for this product. But essentially what we're using that camera for is very much the same thing I showed you in the previous video. We're detecting and tracking naturally occurring landmarks in whatever room that you're in, so we don't need to change the room in any way. We track the landmarks. The fact that we're doing that with an omnidirectional camera makes it all work better. In this particular application of robot vacuum cleaning, we don't necessarily mind, where those landmarks are. They're just fixed point things in the world. What we really care about is the position of the robot. But building this map of landmarks is the means to enabling us to get really accurate real-time positioning estimates of this robot, everything running on board, of course. And that's what enables us to clean the room in a very systematic way. And at that time, that was really new in robot vacuum cleaners. So, other robot vacuum cleaners are available, and they also use similar methods in many cases these days. But this technology has been useful in other types of areas. Some of them you might think of as robots, such as drones. Others you may not think of as robots. So one that you probably just saw or tried a minute ago was a headset, a Meta Oculus headset. When these type of devices first came out, you had to install some kind of infrastructure in your room for them to be able to track their location. The way they work now, as this video nicely shows, is basically through Visual SLAM. So there are cameras built into this thing. They're looking out into the world, and then they're tracking a map of naturally occurring landmark features that they build in. So that it also uses an inertial integration, so it has inertial sensors as well. But the main job is done with Visual SLAM. So I think these are amazing products, but they're really just the beginning of this whole area. So my kind of argument is that this technology of Visual SLAM is gradually evolving into something bigger, and that's what I describe by the term spatial AI. So really by spatial AI, I mean the kind of capability, primarily driven by vision, but certainly with other sensors as well, for a device like a robot to automatically build enough of a representation of the scene around it to really enable intelligent behavior. So if you just build a sparse map of landmarks, that's probably good enough to help you localize where you are. If you really want to do intelligent things, like maybe, clean a whole room, to tidy up a kitchen, to do really advanced things, you need to know much more about the world. I think you need to know detailed geometry. You need to know, the identities of objects and the meaning of things around you. So one way of thinking of that is kind of adding layers of capability, from localization to dense mapping to semantic understanding, and possibly others. But I would argue that this work we've been doing on SLAM, where we focus on real-time operation, really kind of demoing things with real cameras and real hardware, is still a very good basis for this. And I really think of it as, rather than SLAM is done and then we'll add some layers on top of it, I think of it as the SLAM problem evolving, because every time we kind of change the representation, we find new ways that helps localization, that helps mapping. Everything feeds back on itself. So this is an area I've thought about a lot. In general, I've got some discussion papers about this, kind of white papers if you're interested. They're called Future Mapping. There's a couple of them, which really describe what I think are the properties of spatial AI. So, fundamentally, I think representation is important. I think something probably close to metric 3D representation of the world is a generally useful thing, especially for very kind of long horizon tasks. And that maybe the properties of these systems are fairly common. Another kind of key aspect for me is efficiency. So I think, as well as aiming at SLAM methods and spatial AI methods that are accurate, we should also really be thinking about the efficiency. And I'll talk about that a little more later, because that's really important to how practical they are. But I'd just like to show you a few of the steps we've been taking in our lab, in the years since that early work was done, to really build up through the levels of capability here. And these advances have been driven by, partly by algorithmic improvements, new cool mathematical ideas that we and others have come up with, but also by, just improvements in the technology available to us. So in particular, the processing power we can throw at these things has clearly grown through things like GPUs. There's other things like sensing hardware has improved, and then also, new methods of machine learning especially have become important. So first of all, just thinking about new processing hardware and new sensors. So this was a system we actually published back in about 2015. So it was shortly before that time when we founded the Dyson Robotics Lab at Imperial College, which is my academic lab, but which has been funded by Dyson in collaboration with Dyson. This is one of the first pieces of work we published. It's a real-time dense mapping SLAM system. So this is still a real-time system. It's still based on a handheld camera flying through the scene. It's actually an RGBD camera. So this is a camera like a kind of Kinect gaming camera that captures both color images and depth images based on infrared. So the input is basically these two streams you can see on the bottom left. The output of the system is, first of all, an estimate of the motion of the camera. So that's all just coming out of the software here. And so this little purple shape you can see flying around is the estimated position of the camera, updated at every frame. And then this dense map that we're generating. So you can see that this is now very different from the sparse map of landmarks you saw in MonoSLAM. We're now really trying to estimate the geometry of everything in the scene. And in fact, there's many different ways of representing dense geometry, and we've done work using nearly all of them. This particular one, it makes a map using a circle representation. So it's actually lots of tiny disks. If you zoom in on this, there's actually several million disks, each of which has a 3D position, an orientation, and a color. And if you kind of splat lots of those close together, you get this sort of close to continuous looking surface representation. So here you can see that we're really capturing detailed geometry of elements in the scene, like the shape of this chair, for instance. But actually, in terms of representation, this is still just geometry. It's basically just a list of points. There's no sort of sense of meaning here. So that's one of the things we've really been focused on recently, and in fact, a lot of the research community. So adding meaning to representations, or we often call that semantics in SLAM and mapping. And this is one of the areas where methods from deep learning have been very useful to us. So in fact, up until about this time, I'd never done anything with deep learning. All my methods were based on just, probabilistic state estimation, basically. Deep learning, though, allows you to have certain tools that can do things that we didn't know how to do before. So for instance, how do you take a photo and label, what type of objects are present? Is there a cat there and a dog there? Okay, there were hand-designed algorithms to do that, but they didn't work very well. And it was very clear that learned methods were much better. So one of the first systems that we built in this direction was called semantic fusion. So this was published in 2017. So it's essentially a combination of the previous mapping system that you've seen that makes a dense circle map with then a neural network which had been trained for semantic segmentation. So we're taking most of the image frames that come in, and then we're running a neural network that's been trained to predict the category of object that's present at every pixel, and then we take those labels and we project them back out into our 3D map. So if there's an element of the scene that's observed by several different views of the camera, and in each it will gather a label. We then fuse all of those labels together to get hopefully a better estimate of the kind of class of every point in the scene. And this worked kind of somewhat well. These are some kind of results you can see here with different colors representing table and chairs and floor and that kind of thing. Still somewhat kind of messy, and you can also probably see that there's no sort of idea of separate objects here. So, the whole blue area is just chair. And it's like we've taken our elastic fusion map and we've just kind of painted it with this semantic labels. So another piece of work we did was much more explicitly trying to make maps of objects explicitly. So you can really think of this as an object level SLAM system. So we've done, let me just come back to that in a sec. We've done several pieces of work in this direction. And really the key question is, how much prior knowledge do you assume here? So in this case, we're making rather strong prior assumption that we know that there are certain types of objects present in this scene. So in particular, cans, bottles, mugs, and bowls. So for each of those categories of objects, we have pre-trained a neural network which basically has many CAD models, for instance, of mugs, and learns basically the shape space of mugs. So in fact, a mug has a classic kind of shape and then several low-dimensional degrees of variation. So for instance, it can be a little bit wider, a little bit taller. The handle might be a bit curvier or something. So you learn basically a low-dimensional kind of code that can represent those degrees of variation. And then at runtime, we move the camera around. When we detect instances of these objects, we bring in this learned model, and then we optimize these parameters to get a precise fit. So you'll see that we bring these objects into our representation here, and then for each one, we're tuning these parameters so that they fit the observations that we are making. And this gives us then this really kind of efficient and useful model of the scene that it's really just a map at the level of objects. And an example of what we can use that for is some robot manipulation here. So here's an example where we've got a camera close to the gripper of this robot arm. We take a couple of observations of the scene. On the top left here, you can see, if you like, the digital twin of this real situation here. So these are our estimated identities, positions, and shapes of all of these objects. And then we're just using some off-the-shelf motion planning here now to pick up and place these objects. And you'll see that the fact that we have full 3D understanding of this scene means that we can do much more than just pick up objects and drop them. We're able to pick them up and place them very precisely. So stack all the bowls in order of size, for instance. Now, of course, that system is still quite limited in various ways, and it can only deal with those specific types of objects. And I think doing something similar with all types of objects is still a very much an open challenge. So there are other ways that we've looked into, bringing machine learning methods into SLAM. Some that have been really interesting are actually really surprising to me when these happen. So if you've heard of papers like NERF, neural radiance fields, that kind of introduced this idea of actually directly using a neural network as a scene representation. So not just as a way to kind of churn something and put it into a representation, but in these methods, you actually use a neural network as the representation such that you feed a coordinate in and ask the neural network, what is at that position? So for instance, is that empty space or occupied? What color is the thing at that position, and so on. And these methods are quite interesting. And when they came out, we decided, well, let's try and make a real-time SLAM system that works in this way. So we had this method called IMAP that can actually train a neural network in real time, so in 3 or 4 minutes, to build this kind of representation of a room. So it's similar to NERF. It runs much faster, partly by using a smaller neural network, partly by also using depth input from a depth camera, that helps it, and partly just by being quite sparse in the way that it samples observations. And then actually we followed that up with some work in collaboration with researchers here at Dyson in this system iLabel. So this is actually a neural network-based method that jointly builds both a geometric and a semantic representation of a scene. So we move a camera around, we're reconstructing the shape of it, and you can see initially it has these funny kind of random color blobs all over it, and those different colors are representing semantic categories. And initially it doesn't know anything about the different semantics in this scene, but what we show in this system is by applying very, very sparse kind of label information. So for instance, there might be a user involved in the loop here, a human that's just pointing to a few things and saying, that's the floor, that's the bed. Possibly we were just doing it here with clicks on the screen, but possibly this could be through a wearable interface or something. But the point is that you only really need to label a very, very few things, these sparse points you can see appearing here, and then the network will generate labels for the whole scene, which are actually quite accurate. And the reason for that is that both the labels and the scene reconstruction are essentially generated by the same network, and just the fact that it's a network generating this reconstruction, it likes to generate kind of smooth and coherent things. So because the reconstruction is smooth and coherent, the labels inherit that property, and therefore only a few labels can lead to a full sort of representation here. So I just want to briefly show you some very recent work that we've been doing in this area, really, of joining learning methods with sort of back-end SLAM estimation. And in particular, this is very kind of close to my heart because it returns to this monocular SLAM. So by monocular SLAM, I mean there's no depth camera here. This is just a standard color camera that you're moving around. There's no other kind of information being captured here. And in fact, this interesting fact that, I mentioned that, when deep learning came along, it was interesting for us because it gave us a way of doing some things that we didn't know how to do before. In fact, deep learning can also be very good at some of the things we did already have quite good methods for, but, like motion estimation, for instance. But, finding the right way to put these things together, I think, is still really interesting. So, one of the methods, in fact, most of this work is being presented at the CVPR conference this week by the members of my lab. So one really interesting thing you can do with a neural network is predict normals. So by normals, we mean the surface orientation. So here's an example of an input video, and then here on the left, you can see the output of our algorithm, where the color of every pixel here is indicating the direction of the normal. So for instance, that kind of pinkish color is obviously the orientation of the main plane of the wall there. And you can see we're getting these very sort of crisp normals coming out of here. And this kind of runs easily in real time, on a laptop or something like that. So it's a fairly efficient CNN algorithm. So that's just a single neural network running on single frames. This super primitive, another method we're presenting at CVPR this week, is a method that now uses this to build a SLAM system. So I think of it as just a really, really kind of strong prior that helps us with SLAM. So the way it basically works is we we take an input image, which is part of a video stream from a moving color camera. First of all, we segment it, and this is also using an off-the-shelf neural network, the segment anything model that turns the image into chunks that kind of correspond to objects. Maybe they're over-segmented. That doesn't really matter too much, but they're object-like chunks. Within each object, we predict the normal field, and then because we've got the normal field over this region, we can locally integrate the normal field. So normals are just lots of orientations. We can kind of add them all up to get a local estimate of the shape of the object. But we have this one kind of unknown thing, which is we don't know whether this object is a sort of small thing close to the camera or a large thing that's far away. So we've got this sort of depth uncertainty from just a single view. But then if we have multiple views, we can bring in our kind of SLAM-like optimization. So here's a visualization that we don't know whether this blob here, we don't know how far away it is from the camera. But each of these hypotheses of how far away it is projects to something different in this second view. So basically, we adjust that guess until it lines up in the second view and the colors kind of match up. And then obviously, we do that not just for one of these blocks, but for many of them simultaneously. And then we can get this kind of full, really sort of detailed and smooth reconstruction of scenes just from a moving single camera. So I'll just show you one more of these things. So this is something quite different. So another kind of trendy thing going on in computer vision you might have heard of is called Gaussian splatting. So this actually, in my mind, this isn't a neural network method. It's a way of representing scenes with lots of blobs, basically. So in many ways, it's quite similar to the old elastic fusion thing where we represented scenes with lots of disks. Instead of disks, these are now sort of elliptical blobs that are also kind of soft. So that's why they're called Gaussians. They have a Gaussian distribution over their kind of occupancy. So each one has color, it has a sort of density, and it has a position and an orientation. And then as we move our camera around, we're representing the scene with this kind of cloud of blobs, and then we're continuously sort of rendering what the scene should look like from our current map of blobs, and then we're optimizing the parameters of the blobs in order to make it more accurate. So this, these are the images we're capturing, and then, sorry, just go back to here. So, these are the current live images we're capturing. This is our current rendering of what our blob map looks like. If this and this are not exactly the same, we'll keep optimizing the blobs to try and make it a bit closer, and simultaneously track the motion of the camera. So this is another sort of very powerful new technique. It does require rather a lot of GPU horsepower, but we can run it live on a laptop's style system at the moment. So yeah, lots of work going on in that area. And one last thing in that kind of space I'd like to show you is some other recent work, which kind of comes back to close to our interests with Dyson on how these sorts of systems could be used for advanced robotics like manipulation. Here we've looked at object fitting against this sort of real-time reconstruction. Actually, we're using a sort of variant of the NERF type of method here, which is called instant NGP. So this is an algorithm that just from a set of color images, which here we capture automatically from a robot arm. There's a camera mounted on its wrist. We can reconstruct this color kind of reconstruction, and then also a density field reconstruction. So here the kind of whiteness of every position is showing how dense we think the material is in that place. And you can see that this is not perfect by any means. It's got lots of places where there are kind of holes and imperfections. But what it does capture really well are all these kind of real detailed aspects of objects about the edges and so on, and even for kind of small objects like screws and stuff. So what we can then do is, if we've got prior knowledge that we know certain types of objects are present in this scene, and in particular, we're assuming here, very precise prior knowledge of the objects, like we have CAD models of what they look like, then we can actually fit those objects and get millimeter accurate position estimates, even of sort of tricky objects like screws and nuts. And so that might be really useful for object manipulation of interesting types in the future. Okay, so I haven't got too long left. So I'm just going to quickly talk about this last few slides. So, I mentioned earlier I'm really interested in efficiency, and that's actually really key to a lot of the applications we really want to get to in the future. So like lightweight robotics, maybe also wearable devices that can be really small and lightweight. A lot of these systems are still relatively heavyweight, so I'm really interested in how we can get to much more efficiency. I've worked quite a lot, in particular on this Pamela project was a collaboration project thinking about how SLAM algorithms relate to the processes that they run on, and which aspects of SLAM algorithms are the tricky ones to deal with, which ones are parallelizable. And I've really also learned a lot about what's going on in processor hardware. So things like GraphCore in Bristol, I think, are doing really interesting things in developing new types of chips that are massively parallel, but with different sorts of parallelism from GPUs. And that's led me to become very interested in general algorithms that can operate on graphs, which can estimate things in a more distributed way. If you're interested in the details of this, we've particularly gone deeply into a field of algorithms called Gaussian belief propagation. We've got an online article. It's at gaussianbp.github.io, where you can really investigate this, and it has lots of kind of built-in demos where, for instance, you can show that if you're solving a problem like this, where you've got 9 different devices, you might think of them as robots, and they're making measurements of each other, and they all want to estimate their positions globally, but without needing any sort of centralized computer. They can do it basically by passing messages between them, and then all get to a high-quality estimate without needing any central control. So I think that's important because I think it's the route to really efficient computation in the future. So whether you're taking something like a graph processor and trying to distribute the computation across many, many tiles of this processor and trying to get the best answer that you can, or even in kind of related problems, like you've got many, many robots in a space, so similar to what Sabine was talking about, and they would all like to estimate their positions, or they would all like to plan joint action, but without any central controller, by peer-to-peer communication. I think these sort of algorithms are very promising for localization or planning. Okay, so just to finish, this area, spatial AI research, I remain extremely excited about it. I still think that this idea of representation is key. So how do we build representations of scenes that really enable general intelligence? Efficiency is important, and whether the representations are actually useful for the tasks in the end. And that's probably a question that you would ask me. So yeah, in the end, the goal is not to build a map. The goal is actually to do something. And I would agree that there's still plenty of questions there. And then my current interests, very much distributed algorithms and things like sensing and processing hardware. And just to mention again, so yeah, I run the Dyson Robotics lab at Imperial College. So this is an academic lab. We're all, Imperial College members, but thanks to our, fantastic relationship with Dyson, over many years, that, we have an ongoing and excellent collaborative relationship with researchers here at Dyson. So thank you very much.
Thank you, Andy. Questions? We have a few questions here.
Thank you very much. I'm just interested about the Gaussian belief propagation graph work. 2 questions. One is probably more practical. If you have multiple robots, do you need to assume, how do you estimate the uncertainty? Because you are basically passing messages. You are trying to reduce the uncertainty, I believe, by passing messages. Do you assume the robots working in the same coordinate systems, or if they don't have the same common knowledge in terms of spatial coordinates, would that still be possible?
So in the work we've done called Robot Web, which is multi-robot localization, so there's a single global coordinate system. All of the robots start with unknown estimates in that coordinate system. They're all trying to estimate their positions in that same coordinate system. You probably need, at least 1 or 2 sort of, you need some source of kind of overall, position. So maybe you need 1 or 2 beacons in the scene, or maybe one robot has GPS or something like that. But then purely by message passing between them. They're essentially solving the joint probabilistic problem of, given all our intermediate measurements, how do we all know where we are within that coordinate system? And it is possible to do that with distributed computation using belief propagation.
Okay, thank you. Another quick question, and probably general question, because we are aware in SLAM there are lots of different methods like EKF, which is the original Dyson work, and the original mono-SLAM work, and also later we have GTSAM, and now GBP, which is your framework.
Mm-hmm.
So I wonder if you can give me kind of hint why a new framework and what is the advantage or which one is performing better somehow?
Yeah, I mean, of course, I've written dozens of papers about SLAM, and then there's other people have written thousands more. I think because we still, there's still plenty of questions. It doesn't work well enough yet. I mean, it's surprising how well it does work. I mean, look at that Oculus headset, for instance, that many of you tried earlier. You can move your head around like that. It doesn't get lost. It works really well. But that system that you could just wave a camera around and build a representation of this scene that allows you to do the sort of things humans can do. I can glance around, immediately know what objects are, immediately think of how I could use one object to interact with another, know how I would plan my route through those chairs to get to the door and that kind of thing. I still think we don't know how to do that yet, and especially not, human brain can do it with 10, 20 watts of power and a high degree of robustness. We don't have artificial systems that are anything like as good as that yet. So there's still plenty to do, I think.
Okay. Yeah. Thank you.
Robotics, the type of stuff you were showing is not my strong area, but two key words you mentioned is very interesting for me. One is getting those normals to the surface, right?
Yeah.
And the other one is depths.
Okay.
Now, the question I have is, have you actually used that information to produce your 3D object in CAD? And you mentioned something like a reference CAD.
Yeah.
What we use in engineering is a standard NERP surface of representation.
Yeah.
Have you actually done that sort of inverse mapping that you know why I'm asking the question, so you can map
like
it and then bring it back to, yes.
Yes, so certainly you can go between all of these different representations, yeah. So if you've got a surface or a depth model, you can then turn that into a mesh and get.
That's
like
very valuable, because I'm not
Yeah.
talking about just a cloud of points, but it's really
Yeah.
something that engineers can work with later on.
Yeah, I mean, you showed a structure for motion example in your.
Yeah, but there's a lot of problems with that.
Right.
In terms of accuracy and getting it back
but
to
again,
our
that
world.
looked like a sparse reconstruction, so you had
Yeah.
a fairly sparse set of points. I think it's these sort of deep learning methods that can basically fill in the gaps. So if you are predicting all the normals in between those sparse points, you can essentially integrate to get a shape of the whole surface. And those sorts of methods work quite well these days. So come and talk sometime. You're at Imperial, right? So
Yeah, I was going to say my postdoc should come and talk to you.
Come and have a chat, yeah.
Thank you.
Yeah, I guess there is a lot of works to be done on using these techniques to create fast meshes for complex geometries.
Yeah.
That would help us a lot.
Okay.
So thank you very much again.
Okay, thanks a lot, yeah.
So our last talk is from our people from Dyson Robotics team. So we have Anthony Waldock and Moise Sani, and they're gonna talk about robotics in Dyson.
Hello, thank you very much. So I'm just going to give you a brief introduction. We're probably not going to take the whole half an hour. We'll leave some time for questions. It was interesting to have Andrew Davison and Stephen present first, because you can imagine that they're at the kind of 10 to 15 year end of the work that we fund. And Mo and I kind of represent the stuff that we're developing now, which is going out into the market, which you can buy today. And so I'm going to talk a bit about how we develop robotics within Dyson and a bit about the products that we're currently selling. There's obviously going to be a big grey area in the middle here where I can't tell you anything about what we're about to release in the future. So any questions about that, I'll just side shoulder those. But I'm happy to talk about anything that we've got out in the market today. So we're going to start a little bit about how we develop robotics here at Dyson. We've been doing it a long time, and certainly, as Andrew pointed out, Charles is in the audience, has been here from the beginning, I think, or near from the beginning. And talk a bit about how we do it. We develop robots here at 3 different sites. Here in the UK, in Singapore, and in the Philippines as well. So here in the UK, we are not based here in Malmesbury. We are based in Lavington, which is just down the road. So we have our own airfield. We don't use the airfield, but we use the hangars there. This is what they originally looked like when they were purchased. They were used in World War II as a World War II aircraft base. They've now, as you'll be happy to know, been refitted into more modern facilities. Again, not very interesting generic picture of the outside. There are not that many pictures of the inside, but I managed to get a screenshot from some promotional videos that we did, which show you a glimpse into the inside of our robotics facilities. And interestingly, you can see the way they're structured. So we have the usual desks that you would imagine in any lab these days. But in the middle and the heart of it, you can see these pens. And we have a number of different pens down the middle here, all with infrastructure to be able to do testing. Because we're very keen in when we're developing robotics here, that it's not just a kind of theoretical exercise or you develop your code. We look at the whole pipeline of this. So initially, we'll be developing our algorithms and software in simulation at different levels of abstraction. But then we want to get some reality on this. You know, how well does that work on our robots? And so you can take a robot, you can run it in the pen, you can reconfigure these pens with lots of different obstacles, lots of different types of facilities to be able to get a good idea of what they are. And just next to this, off to the left-hand side, there's a whole bunch of labs. Well, one of those labs is actually an entire home. So it's a bit like Bristol Robotics Lab, actually, where they've got a home environment where they do a lot of testing. We have a two-story home inside the hangar where we can do lots of testing, all with infrastructure, for example, ground truthing where the robot is and what it sees. So that gives us an idea. Then the great thing is that you can then take these home and then try them in your own home. So we have lots of different trialists who try them in their own home, which my family are definitely pleased about, especially looking at cleaning every day, cleaning on different schedules. So that's really important to us to get real life into our robots to start with. So I'm just going to give you a little bit of history about some of the robots. Andrew Davidson, as he explained, was there right from the start doing consultancy work and helping develop some of these platforms as well. So you saw a bit of a glimpse of the Dyson 360i, which was released in 2014, the first robot vacuum cleaner. But the one he didn't mention was the DC-06. So probably about 25 years ago, when Dyson started developing robotic vacuum cleaners, was the DC-06. And which was about to be released in 2004. But I think it's worth casting your mind back to the technology that was available in 2004, hence why the size and weight of it. You know, the iPhone was only released in 2007. But back then, you know, battery technology, motor technology was very much limited. Which meant it was very heavy, and it relied on things like ultrasonic sensors to do object detection. But you can see the bulge just at the top where we were using the 360 camera. And that has been a constant all the way through. And one of the things for Dyson in terms of robotics has been that investment in visual information. So we've always thought that the richness of camera technology gives us the information that we need to be able to observe the environment, localize the robot, but also in going forward in the future, give us the richness to understand the environment around the robot. So the latest robot that we've released is the Dyson 360 VisNav, which was released last year. It's particularly important that we don't just develop something that can bumble about your house. It is a robotic vacuum cleaner, so we need the performance. And certainly with the VisNav, we've got the claim that it is the most powerful vacuum cleaner in the world. So we want to achieve the level of performance that you would get when you vacuum yourself. There's just a small video talking a little bit about the cleaning side of it before I talk about some of the technology and the machine learning that has gone into our robots.
When Dyson engineers created the robot with the power of a Dyson vacuum, they designed pioneering new technology, like this Dyson hypodymium motor, creating powerful suction. Then they added a full-width motorized brush bar, Dyson's first with 3 ways to clean across all floor types, so it deep cleans your home properly. A piezo sensor monitors dust levels over 15,000 times a second, adjusting power for more suction when needed. Other sensors detect a wall and automatically activate an extending side duct to direct suction to the side, providing effective cleaning right to the edge. While Dyson's advanced dual-link suspension maintains traction and balance, climbing up to 21 millimeters while retaining consistent wheel downforce so it avoids getting stuck. A D-shaped body makes cleaning into corners easier. And its 360-degree vision system sees precisely where it needs to clean, analyzing up to 10,000 data points a second, mapping and navigating intelligently. Equally smart is the My Dyson app, so you can control cleans wherever you are. Only a Dyson works like a Dyson. Buy direct from the people who made it.
In the terms of the promotional side of it. So I was just going to talk about 2 parts of it, really, where we are using machine learning and advanced systems. I think the first, this is an example of our localization system in terms of identifying those features in the environment and tracking those features over time to work out where the robot is moving. Interestingly, we've used machine learning in 2 parts of this. One is to be able to identify objects in the environment, to be able to make sure we can return to those objects. So for example, our dock, where we go back to recharge, we need to be able to identify that in a number of different lighting conditions. And the other side of it that is quite interesting is in terms of being able to use machine learning to do things like make sure all the sensors are functioning correctly. So for example, if someone was to stick some tape over some of the sensors, we need to be able to identify that and understand that that has happened, and therefore alert the user to be able to, either they're going to get reduced performance if they continue to do that, or there will be, we need to be able to advise them how to do that maintenance to be able to remove that tape. So interestingly, those 2 areas are really where we've started to use some of the machine learning in our localization and sensor systems. Another one, which doesn't actually run on the robot, but is off-board the robot, is something that you saw in the example there about the sensing that we have on the robot to be able to determine the dust levels that it's picking up. So we are analyzing the air and the dust that's picked up through the brush bar system, through the ducts, and being able to understand where people are getting the most dust and dirt in their house. Therefore, plotting maps like this. The one you see on the right-hand side here is available in the app. And you get this distribution. And you can understand where the dirt is starting to build up and where it is not building up. So it's really interesting from a user perspective to be able to use machine learning in cloud-based systems to analyze how they build up over time. So that's just a couple of examples that I wanted to pull out of where we're using it. Mo's going to talk to you a little bit now about some of the challenges that we've got and how we've applied some of that machine learning. So over to you, Mo.
Thank you very much, Anthony. I'm Mo Sani. I'm part of the Dyson Robotics MPI team, Upstream Robotics. So in Upstream Robotics, we try to focus on the future products. We try to build the next product that's going to be released in next 2, 3, 5 years. And I'm going to bridge the gap between the research topic that Stephen talked about, and from Imperial College we heard about that, and also the current technology that we have in the robot, released the latest robot last year. So you can imagine a lot of challenges that the classical algorithms would face in building such a complex robot. You've seen a lot of sensors going on, a lot of actuators are happening there. You need to understand the scene, and such a dynamic scene like a home environment that everything could change and introduce a lot of challenges that classical algorithms will be under pressure. One of the things AI is great at is being adaptive to changes, and we are trying to introduce that to our next generation of the robots. The other thing AIs tend to be good at is better in uncertainties. So we are trying to see what sort of benefits AI can actually get into the robot, and we can sell it and release it to the public. And obviously, safety is another challenge that we need to be aware of. We do thorough studies and testing for our products to be safe. And AI could bring personalization to the product. Imagine if your product could learn what are your habits, what are your behaviors, and customize the behavior of the robot to your home. Unique experience for yourself. And continuous learning. As you use the product, you could get better and better experience. So these are the benefits that AI could bring, and the classical algorithms might struggle with. So one example I could talk about to distinguish this classical versus AI algorithms is probably simplest example is a navigation. So the most common or famous navigation algorithm is a DWA algorithm, that if you wanted to move a robot from point A to point B without hitting obstacles, you need to basically come up with all these trajectories, calculate the robot in the next horizon, and see if the obstacle is hitting the robot, is not hitting. So do all these calculations in a classical method. Whereas if you wanted to do this with methods like reinforcement learning, the way is completely different. You need to run these experiments and define these reward functions and punishments and observation spaces, so the robot will learn by itself. So that's the key here, that you are not coding the behaviors there explicitly, and you're waiting for the robot to learn and explore it by its own. And that's the benefit we are getting here, because the robot learned by its own, it's more robust towards the uncertainties in your home. So you can see there, robot, after running lots and lots of the simulation trials, it learns to navigate from A point to B, and basically in a very small neural network, you are able to do that. Now, we talked about all the great things AI can do, and I want to spend a little bit of time talking about the challenges. It's not all easy to do it rightly on the robot, because you have to run them on the edge. So these neural networks, you have to run through different pipelines to make them ready to be able to be executed on the edge. And developing AI algorithms requires data-driven development. So your whole pipeline of the engineering and software engineering should slowly change towards data-driven algorithms. Everything is data, labeled data, training, deployment, infrastructure to keep these models. Sensor accuracy is another thing. Normally in research and simulation, we might assume that the data we're getting from sensors are accurate, whereas in real world, lots of things will affect the sensors, and the accuracy might be different. So you need to take that into account. Robot might see some stuff that has never seen it before during your programming, and coding might go under the cupboard, and all the sensors are blocked. So you need to probably think about those challenges as well. And the level changes might happen, and all your simulated sensor values might go out of the window, basically. So you need to try to simulate all these possibilities while training your agents as well. And the last thing is basically simulation versus reality. So you need to run all these models, which we have a fleet of models. We try to basically make sure whatever we do in simulation translates to reality. And we are basically looking into future of the cleaning homes. And these are some of the other studies that going on in research department here. So thanks for listening. If there's any question, Anthony can help me answer them. I'm not going to be alone here.
Thank you very much.
Thank you.
I guess we're getting there, that joke of robots doing the laundry is becoming like a reality.
Yeah, hopefully.
We can start with Sabine.
Thank you. It's great to see. Thank you. It's great to see. I was curious about the learning on board the vacuum cleaners, perhaps for the future. Is there a willingness to adopt learning techniques in products that go out, and do you need to test them differently from other types of approaches?
Certainly. I think having the advantage of learning in people's homes, I think, is important. I think I'd predicate that by saying we want to make sure privacy concerns are at our forefront. You know, we're certainly I didn't mention it, that I probably should have, with all of our robot vacuum cleaners, all imagery stays on the robot. It never leaves the robot. And we take that very seriously in terms of, you know, we have a camera in people's homes. That's important. And so whether, you know, we want to be able to learn and personalize that process so that it learns more and more about your home and how you operate it within your home. And I think that personalization people are asking for. So I think that's particularly important. I think there is that appetite for that.
We have a question over there.
This may be a little bit amusing. In the future, will the vacuum cleaner has a manipulator attached to it?
Why not? If you want to clean more than the floor, you're going to need some kind of actuator.
Or like the wheels become an extendable leg.
I think there's loads of interesting configurations that you can have for different robots. Yeah, I think, you know, being able to clean the home thoroughly is our mission. So how we achieve that, I think there's a lot of ways to do it. Any suggestions?
We have one more question here.
Hey, so just the RL one, the example you were showing where you were doing the navigation versus the DWA. I mean, I almost wonder if the RL is the first step where it says that this can be solved, but then do you go the next step to actually, you get a solution that fits your objective function. It might just be doing DWA, right?
It might be doing it, yeah.
So then do you just take that solution and apply, or do you use that as a start point to then reverse engineer what the learning algorithms came from?
Yeah, that's a good point. Different possibilities that can happen from there. But the point is, with learning-based algorithms, the first step can happen very, very fast, and you don't have to hand shape all these algorithms to different cases and corner cases. So in the classical one, if I had to put all the obstacles and design my algorithm and tune it for that, this tuning to some degree will happen in simulation. And instead of doing that, I'll spend more time to come up with all the corner cases, but not program it, but let the robot to solve it, basically, yeah.
Since you said you wanted feedback from the people's houses, I don't think my wife's, a robot vacuum cleaner is Dyson, but I haven't paid attention to which make it is. But I can share with you two problems we have with it. It's not just a vacuum cleaner, it also does the mopping. Mm-hmm. But the water reservoir needs continuous changing. So I think my suggestion would be just have something that actually go and change the water itself. So that would be one suggestion. The other one, you mentioned the robots get stuck in a particular corner, and then the latest version has got this interesting shape that can get itself out of the. Well, I can see that, a square versus circular might be improvement. But our robot gets stuck in elevation. So if you have a table that goes up, the robot goes up the elevation and gets stuck there. So somehow you need to have that Z direction type thinking in depth. it has got this tendency of the fall off the floor or go up something. So I don't know, maybe your robot is more clever than our robot, but that's two things I can give you feedback on. And it's interesting, the first question that I mean, I don't know, in Rolls-Royce, we get, although we sell our engines, we continuously get data back from the airlines. So I don't see the problem with getting, learning from the robots that you sold to people and try to learn from these difficulties I shared just now.
I think there's a difference between learning from how people use robots. So for example, what is the typical time to start a clean? How often do they clean for? How big is, on average, are people's houses? Things like that. There's a difference between that and imagery, I think. There's a big difference.
I guess
you could potentially send what you learn from the image back, because that preserves the privacy, right? Because that's the issue. You don't want to send a camera feed from the robot back. A, because it's a huge amount of data, and B, because it's a privacy invasion, right? But you could send the learnings back, right? You could have it anonymized in such a way, or like you've got the processed output, right? So that makes it okay. Yes.
Yeah, definitely.
Any other questions? Okay, so thank you very much again for your presentation.
Thank you.
So this brings us to the end of this symposium. Thank you very much for joining us. It was really nice to have you all here. Thanks for the presenters. Thanks for the people who were joining us online. If you're traveling back, have a safe journey back. We have some fruits and biscuits, some drinks. Make sure that you take some for your travel back. If you're staying here for the night, there are lots of things to see here. Cotswolds is here. Castlecombe is like 20 minutes away. Make sure that you make the use of the night, and hope to see you soon again here at Dyson Institute. Thank you very much. Sorry, just one final point. Don't forget to I just have a request.